Hello. Okay, this is Cope. Pure Cope. Cope. Okay, today's game plan is to learn probability, do some sums, and when I get bored, I need to build something. Solid game plan. Let's go. Let's read a Bible verse before that. Okay. The King Darius issued a decree and search was made. What the fuck? Big one. And a search was made in archives where the treasures were stored in Babylon, and at the Achmeta, in the place where the province of Media, a scroll was found, and it was written thus: in the first year of King Cyrus and King Cyprus, instead of decree concerning the house of God at Jerusalem, let be rebuilt. Let the house be rebuilt, the place where they offered sacrifices, and let the foundation of it be firmly laid. Its height 60 cubits, and its width 60 cubits, with 3 rows of heavy stones and 1 row of new timber. Let the expenses be paid, and the king's treasures. Also, let the gold and silver articles of the house of gold which Nebuchadnezzar took from the temple which is in Jerusalem and bought Babylon be restored and taken back to the temple which is Jerusalem, each of its place, and deposit them in the house of God. Now therefore, Talonel government of the region beyond the river and Shehinah, Bonsai, your companies like the Persians who are beyond the river keep yourself far from there. Let the work of his house, God alone, let the governor be the Jews and the elders be the Jews, build the house on the site. Moreover, I issue a decree as to shall do the elders of the Jews. They, for building the house, let the cost be paid at the king's expense from the taxes on the region beyond the river. This is the given immediate to these men, so they have not hindered, and whatever they need, young bulls, rams, and lambs from the burnt offerings of God of heavens, wheat, salt, wine, and oil, according to the request of the priests who are in Jerusalem. Let it be given them day by day without fail, that they may be sacrifices of sweet aroma of God of heaven, and and pray for the life of king and his sons, and also issue the decree that whatever alters this edict, let the timber be pulled from the house and be erected, and let him be hanged down it, and let his house be made in a refusal heap of this, and may God, who causes his name, dwell with their destroy their king, any king, for people who put their hands on the after it, or destroy his house of God which is in Jerusalem. Darius issue a decree, let it be done delightfully, and Tatani government of the region Babylon beyond the river, and Shahir Bonzai and their companies diligently did according to the king Darius and sons. So the elders of Jews build, and they have prospered through the piousness of Haggai and prophet Zechariah and his son Iddo, and they built and fished according to the commandments of God of Israel, and according to the command of Cyprus, Darius and Axares, kings of Persia. Now the temple was finished on the third day, on the month of Adar, which was the 6th year of the region and King Darius. Then the children of Israel and the priests and the Levites, the rest of the descendants of captivity, celebrated the dedication of his house God with joy, and they offered sacrifices for the dedication of this house, 100 bulls, 200 rams, and 400 lambs, and the sin offered for all Israel, 12 male goats, according to the number of tribes of Israel. They assigned to the priests to their division, and to the division over the service of God in Jerusalem, as it was written in the books of Moses. And the descendants of captivity kept the Passover on the 14th day of the first month, for the priest and the Leviticus had purified themselves. All of them were ritually clean, and slaughtered and the Passover lamb of all the descendants of the captivity for the brethren and priests, and them slaves themselves, and the children of Israel who had returned from the captivity had ate together with who have serpent themselves from the faith of the nations of the Lord, and let us seek the Lord Israel. And they have kept the feast unleavened bread 7 days with joy, for the Lord made them joyful, and turned the hard kings in Assyria towards them, to strengthen their hearts in the work of God. Okay, God of Israel. Okay, sweet little. So this is Ezra 5:9, decree of Darius. Amen. Let's make a short prayer. Father, who art in heaven, I want to study for like 10 hours straight. I want to study. Give me the wisdom. Give me the knowledge. Give me the perspective. Make me be good. Thank you, Lord. Thank you, Lord. Thank you, Lord. Love you, Lord. You're the greatest, Lord. Jesus. Or whoever above and beyond. No, let's not say that. Above and beyond. That's Baphomet.
Here, even though fortified flat worth around 500k with a mortgage. Look, no 500k is a lot of money, but at the price, you ease an area where you don't feel particularly safe, or you end up in some grotty, rundown neighborhood that's not exactly desirable. The second you buy, you become a mortgage slave. For the next 20 to 30 years, every fucking life decision you make revolves around that goddamn house. Once you got a massive mortgage hanging over you, you become what I call an mortgage slave. Someone with a low quality of life, constantly terrified of losing their income. To actually have any breathing room in London, you need two things: a property with a mortgage plus about 40k pounds a year for living expenses. Otherwise, even if you come from a comfortable middle class family back home, then they will have you constantly stressed about money. And if your degree isn't in computer science or finance, you simply won't earn enough to be completely independent. So if you're coming to UK study, you really need to think hard about whether the degree will actually pay. Because when you graduate, then this cost of living will absolutely crush you. Trust me, I've been there. I remember when I first graduated, less than 40k pounds a year. I'd sit there, stare at my bank about quitting my six-figure London job and moving back to China has had over a million views now, and that's when I'm not the only one who's been absolutely struggling with it. I've had loads of. I just quit my six-figure London job. It took me 12 bloody years. I earned a six.
I want to live in London. That's what I want to do.
I earned a six-figure salary in London, and I still couldn't afford to live there. According to IMF data, only the top 3% of UK households earn that much. But here's what they don't tell you. After tax, I took home just over £6,000 a month, enough to survive London, not enough to actually live there. Let me break down the costs. This is a 45 square meter one bath flat. I rented in Huntington, £180 a month. You'd think that buys you safety, right? Wrong. On my first day moving game, someone was murdered outside a building entrance. Every few weeks after that, stabbing, shooting, robberies, always 100 meters. I'm the kind of person who gets nightmares from harsh on posters. Not to mention the movies I fear every single night. Here's what else I paid every month. Tax £80, utilities £100, water service £50, heating £200, Wi-Fi £55, groceries £300, eating out and takeaway £700 to £1,000, monthly two plus £170, mobile £22. I spent over 65% of my post-tax income just to exist in London, and that's about £2,000. But I couldn't actually spend it. Every penny had to go to savings and invest. And otherwise, I'd be working until I literally drop dead. No chance of ever retiring. But the real costs, those are invisible. Every time a friend asks me to meet her, I had first. Steak out starts at £100 minimum to drinks, dinner, transport, Vegas menu. Over time, I started filtering friendships by price. If this person was 100 quid, that became the automatic calculation. In my head, the best friend, my country announced I moved to Paris next week. Getting a high transition to investing in friendship often felt expensive and pointless. The most expensive cost is what you can see. To keep that six-figure job, I had to constantly prove my worth. Every project was competition. Every presentation was full name.
Bro, I think a six-figure job is more than enough, isn't it? Is this bitch tweaking? Living in London. I mean, these bitches, like, they want to live in. I want that city life, you know. Single. Bro, city is way better. These bitches are tweaking. There's so much shit to do in London. Um, bro, these bitches tweaking. You know what I mean? You don't need that much if you're about to take home. So you keep 75%. Uh, Take home, comfortable, very comfortable while sharing. Okay, this is the thing that I'm aiming. So let's see. Yeah. So I got a message from my friend.
Survive here. Even though I push myself to earn over 100k a year, it's still not enough. The fact is, if you want any sort of decent life in London, your family needs to hand you at least 800k to buy property minimum. I've worked in London's tech industry for 9 years. Even though I've been earning six figures for the past 3 years, I can only afford to buy a flat worth around 500k. Look, I know 500k is a lot of money, but at the price, you ease in an area where you don't feel particularly safe, or you end up in some grotty, rundown neighborhood that's not exactly desirable. The second you buy, you become a mortgage slave for the next 20 to 30 years. Every fucking life decision you make. Is exactly what I did. Back home, my family wasn't wealthy or comfortable. I never imagined that moving to London would be going through every struggle I ever faced before. Now, I know some girls go to London, they'll be married will change everything. Fair enough. London's full of wealthy people from around the world. I mean, just look at Prince of. This one mechanism is the
Living in London is the best thing, man. Yeah, I'm kind of like romanticizing it, but why don't you want to live in London? I don't get it. Like, London is pretty expensive, yeah, but it's like everyone who's interesting in life would be found in London. So You could literally make all the connections you want and come back and live anywhere in the world and get the connections. So that's all it matters, right? Connections at the end of the day, if you're like a nice person to be around, they're gonna prefer you more than some random guy, right? So connections is key, and London is the place to get it. And tech is the only job that allows you to actually like be in London without being in complete destitute. It's like let's look at Indeed for a second. Um, salary guide. So let's oh fucking bitch. No fucking way. 60,000, brother. Okay. Hopefully, what do I need to do now? I need to learn. I need to do some problem solving with linear algebra, and that's today's goal. So that is my pen and paper. Today's goal is to do. How long have I spent on this? This bullshit, bro. How long have I spent on this? Okay, 20 minutes on LARPing. Okay, today's goal. Let's see if I've done my previous goals. Chess engine. Okay. Building shit from scratch. Okay. I don't need to do this. Logic paper. Okay, Taylor Davis. I'm gonna do that. Genesis book. Okay, doesn't matter. LinkedIn. Yes. Website SEO. Probably not. I don't want to do this anymore. WhatsApp this guy. Done it. Um, so what do I need to do? I need to uh, reach out for mentorship, email, Excel jobs. Um, it's both are connected. Um, who else do I need to reach out? I need to reach out. Maybe Anuj. Maybe I don't know. I need to. I need to reach out. So right now, I need to do lineage problems and distribution problems, ML. I need to do that. And Docker, DevOps, roadmap, CI, CD. I need to learn that. Systems. Okay. I need to learn that. And I need to do another. So this will be deep work. All of this shit is deep work. Reaching out to people and all of that is like non-deep work. This is shallow work, deep work. What are another shallow work that I need to do? I need to make a call with someone. Maybe I need to call this guy. Let's see. Pa, 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 pa. I need to call this guy. Maybe. Maybe. I don't know. Yeah, that sounds good, bro. Mm, shallow work would be calling people. I need to call another dude. Who do I need to call? Fucking bitch. This is deep work. I need to call this guy. I had to focus all of my energy into like a couple of people. People. Where's people? Yeah. Macha. This guy. There's a lot of the deep learning. It's completely avoidable. I mean, you don't have to, but I think you need to master the ML basics first before going into the deep learning stuff. Who do I need to text? Text. I need to text someone else. Not this guy. Not this guy. Um, I need to text this guy. Oh, scary. Scary texting people. Um, who do I? I need to send a message to someone. Mm, okay, message pretty much sent to everyone. That will be the shallow work. Okay, messaged everyone. Now I need to get a template for our. uh, yeah, I need to find the best template to like cold approach people on LinkedIn and kind of like market myself as I know what I'm talking about. So like that, maybe I don't know. And yeah, get to work. Um. So yeah, let's do some. I'm gonna take a small little break. I get every talent out there, organize them, get to a common goal, and make a difference, right? So I need to do some. I need to reach out. That will be the shallow work. Shallow work is actually fun. I need to get a template, mass send to people, kind of like tailor them to their needs and see what I like about them, and send like a random email. And yeah, I think I need to like text some people too. Okay, I need to even more now that I think of it. Hamza, um, yeah, pretty solid, I would say. That's so I need to what else? Email. Okay, let's do some deep work. Deep work. Um, pa, 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 pa. Bro, all I need is like one friend who's into like ML research. That'd be so cool. But I just don't have the network like that. You know, I need to build it from the ground up. I think I can, but it's gonna be a little bit difficult. But it is what it is. At the end of the day, it is what it is. You know, it is what it is. Cousin. It is what it is. Okay. DSA, you can go back. Don't really need it now. Uh, okay, let's go here. Let's go here. Let's go here, baby. Pa 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 pa. Learning. No deep learning. Only probabilistic ML probability. Okay, binomial distribution probability. Can I do it? Poisson distribution probability. So let's try to do this. So we have. So what do we have? So we have a Python function to calculate the probability of the. Wait. No. We have write a Python function to calculate the probability of the observing exactly k. So what am I doing? I'm returning. What does this do? Let's run this. So write a Python function to calculate the probability of the observing exactly k events in a fixed interval using Poisson distribution formula. The function should take k, the number of events, and I am the mean of rate of occurrence as input and return the probability rounded to 5 decimal places. Um, okay, okay, okay. What the fuck? So for me to solve this, I need to go here. This is Poisson. Poisson. How do you call this? How do you call this? MIT courseware, Stanford. Best statistics. I need to I need to get a deep understanding of the core basics. Everything else can fuck off. Such a perfect mindset. I don't know. I'm just glazing myself at this point. Okay. Open courseware. That is stat. Brother, I mean statistics. Statistics. Statistical physics. Statistical method. Statistical application for statistics. Okay. Oh, fuck. I didn't mean to do that. History, history, history. I'm kind of retarded. I'm kind of. Harvard probability. No. Bro, intro to statisticals. Gilbert Strand has like a statistics course, I'm pretty sure. computational. Learning mathematical differential equation and linear algebra, engineering math, the fuck, calculus online textbooks, linear algebra, highlights of calculus. I don't want to learn calculus, bro. I do need to learn calculus, but right now at this time, calculus is my least of my concern. Let's go here. Uh, Statistics and probability of combination for biologists. I don't need it, bro. Don't need it. Intro to statistics. Is it a application statistics? What is going on? Oh, this guy. Lecture videos. YouTube. Mighty. How to get professors to review your proof and get feedback. I think I know how to do it, but probably later in PhD stages type problems. It might? Question mark. I'm pretty sure. Yeah, yeah, yeah. So yes. Okay, okay. Oral theory. Okay. Um, say the professor is challenging but fair. Saying the professor does not look good to their bosses. Say the professor motivated you. Just in case, maybe with a specific example, like okay. Bad evaluation, Fally. Thanks to the writer for the reference sake. I reminded. Okay. Proofwriting. I need proofwriting. Stanford. Statistics learning with Python. Is it free? Okay, I need to write it down. I need to approach math people. I need to approach smaller math people for proofwriting. Okay, frame it around. Accept silence probably. It means he's busy and also kind of work used to form. Okay, okay. I need to do that method. Smart. Okay. Cool. Statistics and probability. I need to take the initiative on that for sure. No, I don't need this in the college course. I'm still not working though. I'm still. It's been an hour. Still haven't put my back.
Welcome to the first lecture.
Intro to. Okay. Interference and LLM estimations. Okay. Intro to Bayesian. Intro to classification. Central limit theorem. Markov-Chain Poisson. Ooh, nice. So I need to. What should I focus on first? Probability or statistics?
In this lecture, we introduce the Poisson process, which
The thing that I hate about the MIT shit is. Okay, I need to. Fuck, I need to learn probability. I need to learn statistics. Holy shit. It's gonna take me some months. But it's fine though. Let's see. $10 a day. Boom. You can get deep level analytic probability and statistics in 14 weeks if you're disciplined. So that's cool. Okay. Um, Probability models and axioms. That's cool. You know.
Welcome to the first lecture of this class. You may be used to having a first lecture devoted to general comments and motivating examples.
Bro, this is AI. No way.
This one will be different. We will dive into the heart of the subject right away. In fact, today we will accomplish a lot. By the end of this lecture, you will know about all of the elements of a probabilistic model. A probabilistic model is a quantitative description of a situation, a phenomenon, or an experiment whose outcome is uncertain. Putting together such a model involves two key steps. First, we need to describe the possible outcomes of the experiment. Of this class. You may be used to having a first lecture devoted to general comments and motivating examples. This one will be different. We will dive into the heart of the subject right away. In fact, today we will accomplish a lot. By the end of this lecture, you will know about all of the elements of a...
Wait, what is the all the distributions that are needed? Okay, okay. What are the? It's all probability distribution, right? So I'll put my Bible over here. Take mine. So this is types of. So is distribution probable? Wait. I need to get Math GPT. Math GPT is probability or stats describes distribution question mark. Fuck. Whew. Almost broke my laptop. So probability is a described distribution, but they do it in a different direction. You can see it in okay. What should I learn? You should learn them together, but start with probability first. Think of building a house. Okay. Foundation of probability in ML and probability is a mathematical framework representing uncertain statements. In ML, we use to qualify likelihood of outcome, n of n key terms, n of n samples, set of all possibility outcomes, n of random variable x, and a variable whose values depends on the outcome of a random phenomenon in probability math function PMF for discrete variables p of x is equal to the nf probability function PADF. Continuous variable f of x is a normal distribution n defined by mean and variance. Okay. Applied statistics for ML involves collection of analyzing and interpreting data patterns, making inference, descriptive statistics, summarizing data using central tendencies and dimension and inference and statistics, drawing conclusion about population from sample and hypothesis tests using p-values, of course, to determine the results of statistically significant. So these bitches in all these microbiology and biology fields, they just like fuck with the p-value all day. So M of maximum likelihood, MLE, maximum likelihood. This is the weighted lines drawn. A method to estimate the parameters probability maximum likelihood function. How they emerge in machine learning, and machine learning models are essential statistical models that learn from data, Bayes' theorem, and the bridge between probability and learning. Okay, the loss function is the mean squared error to a distribution, normal distribution, and an evaluation, and using statistical metrics like precision, recall, and F1. Okay, cool. Best approach, Late's Raji probability function, and on our rules, basic distribution, basic statistics tools, learn mean variance model. Okay. Combine ML. Start learning ML algorithms when you hit a concept you don't understand, like maximum likelihood estimation. Go back and study. Okay. Study recommendation. Probability basics, descriptive, where to learn descriptive stats. Fucking hell. Descriptive stats. I just don't fucking probably somewhere. So I need to learn. That seems like a decent order. Wow. A descriptive. I don't know how deep I need to go with all of this. That's like the bigger issue and all of that. I need to kind of like come up with my own. That's like the best thing to do too. Just like out of principle, coming up with your own ideas is way better than kind of like regurgitating whatever the fuck they want you to believe. The elites. So this is poison. Okay, let's chill out. Let's try to like solve this shit. Uh, the function calculates the probability given an occurrence in a fixed interval based on the mean rate occurrence. So explain the question. To understand this problem, we first need to understand what's Poisson distribution is. Imagine you're standing at a bus stop. You know that on average, 5 buses arrive. Fucking nigga, don't do that. Average 5 buses arrive every hour. Okay, 5 buses arrive every hour. However, some hours might take 3 buses and some might take 8 buses. The Poisson distribution is a mathematical rule that tells the probability, the chance of a specific number evaluating on a so on k. So we already know that the average rate the lambda is the average rate. I need to Poisson distribution. Uh, Bernoulli distribution, it's let's say it's a weighted coin. You can think of it as a weighted coin, and like I don't understand how the formula are derived, but anyways. So lambda, okay, k, specific numbers of event, want to check what are the chances of exactly three buses. So k, I thought, okay, specific எவ்வளவு வருதுன்னு பார்க்கணும். Okay. Okay, p x is equal to k lambda, so a random whatever k dot minus. How the fuck did he come up with that? Like, fucking impressive. So that's the formula for Poisson distribution. So we have, and we need to return the rounded value of these two. Let's reset it. I don't think I actually did. I write that code? Probably. So yeah, this is Poisson distribution. So lambda would be 5. So there's like 5 buses coming by at a certain bus stops, and on average. So let's draw a graph, whatever. On average would be like middle, right? The middle of the area. That's like 5 buses coming every hour. And they're asking, what are the chances there are 3 buses? No. The graph is wrong. Let's say it's like this or whatever. On average, there's 5 buses. They're asking what happens when there's 3 buses. What will be the function to calculate how many, wait, distribution, the probability distribution of what happens here. Okay, I think that's what it is. So let's say this is the line 1, 2, 3, 4, 5, 6, 7. Okay, you have a number line like this, and they're asking what happens here, how to find this output, and what function it is. So this will be on average, meaning 0.5. So this will be somewhere less than 0.5, I think, right? 0.4. What is the probability of that happening? So the formula is so it needs to be a for loop, from what I can tell. So for I in range k will be the number of events happening. Should it be k, or it's hard to tell? It's hard to tell because lambda is the average. So I think it should be range. Let's try a range of lambda just for the sake of it. I don't know. I'm just a goyim, I'm goy maxing. Okay. So we have this for I in range of length of len of lamb. So let's say it's 5. Oh, I don't need len. Just so let's say it's 5, and I'm iterating 5 times, and I'm stopping right. So mm, if it is bigger, if k is bigger than lamb, right? If k is bigger than lamb, I need to do something. If else, I need to like go through the entire loop. So if it is bigger than this, if the probability is bigger, if the occurrence is bigger, I need to run another loop, maybe for j in range of k, and I need to go over a loop somehow. And for else, hmm, what should I do for this one? For else will be just give me the formula. Sticking at your tongue for the Rizzler. Okay. Give the Python code for this. Let's see. So y is lambda, the average. So the lambda will be the average, and k will be the average occurrence, right? It's something have an occurrence of a event like taking a shit, taking a shit at office hours, and the average rate number of events, number of taken shit on a period. Okay, whatever. That's how I like to imagine. So taking a shit and no, don't do that. Don't do that. Okay, in NumPy, nigga, in NumPy. So we have y is minus. Okay, how do I derive? Duplicate, reset. So let's. That is taking a shit. This is flipping a. How do we derive it though? Bernoulli, how do you derive it? Let's see how do you derive it. So starting at the binomial distribution, okay, where k is equal to where and why is that? We're substituting this to this. We're just taking the limit on three parts, fundamental. Okay. And man, MathGPT is golden. It has some issues. You're very close, but there are two fixed math only. Okay, I need to Poisson distribution.
In this video, we're going to talk about how to use the Poisson distribution formula in order to solve problems. So take this problem, for example. A small business receives...
So, okay, 12. What probability that the business receive in one day? On average, bro, this is like so practical too, isn't it? So on average, let's say I get two matches a day in Hinge. Okay, like five matches a day in Hinge, and the Poisson distribute. So what is the probability that I get 8 matches in a day, right?
On average, 12 customers per day.
Put this shit here. The derivation is the difficult part.
What is the probability that the business will receive exactly 8 customers in one day? So the first thing you want to keep in mind is that
It's pretty Poisson distribution. You're deriving it from binomial distribution too. So yeah, doing it in a linear fashion is kind of usually. Here's a clean and correct solution of the Poisson distribution. Nothing hurts anymore. I feel kind of free to see if I still breathe. Yeah, nothing hurts anymore. I feel kind of free. Could see you used to. Yeah. Factorial k, probability round. Okay, we're just rounding up to 5 decimals, it seems. Uh, the thing that I hate about it is like math.factorial.k, right? Yeah, I guess so. Math.exponential minus lam multiplied by lambda power k. That's the probability of the function. Okay. How am I going to remember that? So this is the probability of the function. So k, they're giving k to you, they're giving lam. So what is this? That is the probability, and I need to return. Yeah, what's wrong with that? Print. Probability. Delete 0. Probability. What is the outcome? No, I copied it. Oh, it's gonna be like a really long number. Do they need it? Is that how it is? These are like easy questions, though. I'm not really like implementing anything new. Just printing a probability distribution on a thing and calling it a day. Um, what is going on?
That the time interval is the same. It doesn't change. So thus the mean is 12 customers per day, or the average. Now some textbooks will use lambda for the mean. I'm going to use this symbol here. X is what's the probability? And the formula is mu raised to the x e to the negative mu divided by x raised to 0. And 6 times 0 average probability.
Okay, student receives 7 text messages a day. This is gonna be good. So 7 text messages a day in 2-hour period. So on like a 2-hour block, he receives 7 text messages. What is the probability that the students will get 9 text messages? So in 2-hour period. Does the period matter? So the period remains the same. So I don't have to do anything different. So it's going to be on average. On average is 7. So it's going to be 7 by 9 into minus 7 divided by 9 factorial. I think that's about it. And what is the probability that the students will receive exactly 24 message in an 8-hour period? So getting this 2 hours, we have 7. Okay, that's the average. I don't know why I'm putting this here. I don't get it. But they're asking exactly 24-hour. What will the probability that the students receives exactly 24 messages in 8-hour period? So the probability of a student getting 24, the p of x, the x is going to be am I just going to multiply? I don't know. I don't know the answer for the second one.
Go ahead and try it. Now, there's something that clearly see that 7 divided by 0.1014, which correlates to approximately.
That's what I did, right? Yeah, that's what I did. Okay.
10.14%. Period is 8 hours. So by looking at these values, you can
just doing a normal linear So 4, 3.5. What?
See what it is. Therefore, we need to multiply work out as nicely as what we see here. So you can set up a proportion. If you want a formula to do this, you can use this one. We're trying to calculate t times 8 is 50. Divide both sides. What we know x has to be 24. We want to calculate the probability that the student will be seeking for. 24. That times e x factor 0. So number of calls per hour. What is the probability?
What do we have here? A small business, like whatever, 8 per hour. 8 per hour. What is the probability that business will be 7 calls in 1 hour? Just plug that shit in the thing, bro. It'll be 8, 7, e minus 8, 7 factorial. Okay. What is the probability the business most calls? What is the probability that the business will receive at most 5 calls in 1 hour? At most 5 calls in 1 hour. So it's gonna, I'm just gonna add the probability, I think. So it's gonna be, yeah, it's gonna be like, we're just gonna add x of 1, x of 2, x of 3, x of 4, x of 5. We need to add all of the 0 point shit. It's gonna be some 0 point shit like that. What is the probability the business will receive 6 calls in 1 hour? Same thing. Average 8, okay.
That the business as a listen. 5. So that's the answer for what is the 5? Now mu is still. So we want to say that x is going to be plus the next one where x is equal to 1. We have to add up the individuals. Mu tx. Now x is going to do something over x less than or equal to 5 is going to be e to the negative mu, which is e to the negative 8, and then times, we're going to plug in these values when x is 0. So mu is always 8, raised to 0 power over 0 factorial, plus, now when x is 1, that new value, and then when x.
So what is this formula over here called? I think the probability, okay, it's summation, okay, whatever. It could be written in, how can.
X is 2, and so forth. And then you can just follow the pattern. The part in 6 calls in 1 hour. So 6 has a graph that is decreasing over time.
Oh, more than.
The probability is on the x, I mean, it's on the y-axis. The random variable x is on the x-axis, so the horizontal axis. Now let's say x is 6 at this point. So we're going to split the graph into 2 parts. Let me use a different color. Now let's say it will be 70%.
It's, yeah, 8 is going to split the graph in half.
Because these two halves have 200. So on the left side, this represents the probability that x is less than or equal to 6. On the right side, this represents the probability that x is greater than 6. Now, if we add these two values, this is going to equal 1. So if we take this term, move it to this side, we say that the probability that x is greater than 6 is 1 minus the probability that x is less than or equal to 6. So this is going to equal 1 minus the probability that x is 0 plus the probability when x is 1 all the way up to 6. And I'm going to space. So this is going to be 1 minus, we're going to use the same speech again in part B. So it's e to the negative 8, and then times mu 0, mu to the x over x factorial. So mu is 8, x is 0. And then plus 8 to the first power over 1 factorial, plus 8 to the second power over 2 factorial. And we're going to repeat this until we get to 6. So go ahead and type this in.
Bro, why did I? History, probability, statistics, fucking nigga. Okay. Problem set, midterms exam, final exam. Bro, what the fuck? What the fuck? What you talking, bro? Uh, six. Position. Continuous random variable for two. Okay. Give me linear model with noise Bayesian interference, central limit, introduce classical statistics. Okay, classical Poisson. Where is Poisson? Bro, ain't no way Poisson is over here. Bernoulli process. This is classical statistics. We're in the statistics area. But why? I don't know.
In this lecture, we introduce the Poisson process.
22. Uh, Poisson. Okay. I just hate MIT courseware.
In this lecture, we introduce the Poisson process, which is a continuous time analog of the Bernoulli process. One way of thinking about it is as follows. Time is continuous, but conceptually we divide it into a very large number of slots, and during each slot we have a tiny probability of an arrival. This probability is proportional to the length of the slot. Furthermore, we have an independence assumption for the different slots. The Poisson process is a very elegant model of arrival processes in continuous time. It models many real-world phenomena, and it also has a very clean mathematical structure that allows us to calculate
Arrival. Okay, I don't have to write it down.
practically every quantity of interest. Our development will parallel our analysis of the Bernoulli process. For example, we will find the PMF of the number of arrivals during a time interval and the PDF of the time of the kth arrival. We will discuss the memorylessness properties of the Poisson.
So K is just a number of trials, or like the number of outcomes. So, okay, the number of outcomes. K is the number of outcomes. That's what you're trying to find. Okay, K is the number of outcomes, number of times you've taken a shit, whatever. N is the number of trials. So if you have some okay, that is Bernoulli or binomial distribution. That's binomial distribution. Okay. Frequent probability distribution, discrete central limit, basic probability. Uh, so this is the mean x. Okay, mean. What the fuck is variance? So let's say an average. We take 5 shits, 4.11 coffees a day on the office. So fuck. So the x will be the function. So it's 80% likely that you get. Okay, it's not 80%. It's actually 1, right? 4.11. Why is it 80%? So if that is average, okay, on average you take, so it should be like 5, right? Oh, it is 5. Okay. It is 5. Okay. Cool. So on average, so okay, this is the 50%, right? So around 50% of the time, you take 8 coffees a day. So the number 8 will be in the, this is the number, right? No, 50%. This is 50%, right? So let's say K, so let's say 2% is literally 0. It's literally like 10% or something. So if I like zoom in really, really nicely, let's say 2, it is literally really, really tiny. So that's the underlying idea. So let's take, this is 200%. So Poisson distribution, it contains within 100%. Okay, 200% doesn't work that way. So this is, what is 100% likely? So 50% of the time you drink. So 50% of the time you drink 4.5 coffees a day. Okay, and why is it keep going up though? Shouldn't it like kind of come down? I think it kind of comes down. So okay, X is just a continuous, or it's a discrete too. It's a discrete probability distribution that keeps on increasing. Okay, I think that kind of makes sense, but it doesn't. Let's just look into the solution, bro. Let's just look into the solution. Brody, literally what I wrote. Literally what we wrote, bro. And the deriving of the function is more important than the actual thing. So yeah, there you go. So how do you derive it? How do you derive a function like Poisson distribution? I don't know.
Poisson process. Similar to the case of the Bernoulli process, this is just a consequence of the independence assumptions that we are making.
So yeah, everything is independent too. Okay, every process is process independent.
We will then exploit these independence properties to argue that the interarrival times are independent exponential random variables, and we will conclude with a comprehensive example. We now set out to study the Poisson process, which is a continuous time version of the Bernoulli process. In the Bernoulli process, time is divided into slots, and during each one of the slots, we
Is it a wait? It is discrete. The process is continuous. What the
may either have an arrival or no arrival. In the Poisson process, time is continuous, and we may get arrivals at any time. We want to define the Poisson process by introducing some assumptions that in some ways parallel the assumptions that we made for the Bernoulli process. What were those assumptions? The first one we made was the assumption of independence. Slots are independent. Similarly, for the Poisson process, we will make the following independence assumption. We will consider two intervals. Time intervals that are disjoint, and look at the random variable that stands for the number of arrivals during this interval. The different slots are independent.
Well, let's just switch this. Switch this to this.
Time is divided into slots, and during each one of the slots, we may either have an arrival or no arrival. In the Poisson process, time is continuous, and we may get arrivals at any time. We want to define the Poisson process by introducing some assumptions that in some ways parallel the assumptions that we made for the Bernoulli process. What were those assumptions? The first one we made was the assumption of independence, namely that what happens in different slots are independent. Similarly, for the Poisson process, we will make the following independence assumption. If we consider
It is independent, yes.
two time intervals that are disjoint, and look at the random variable that stands for the number of arrivals during this interval and that interval, we will assume that these two random variables are independent. But even more than that, if we take any collection of disjoint time intervals and we look at the associated random variables, the associated numbers of arrivals, that collection will also consist of independent random variables. The second assumption for the Bernoulli process was one of time homogeneity, namely at each slot we had the same probability of an arrival. We want to make a similar assumption for the Poisson process, and it's going to be the following. The probability that we have k arrivals during an interval of a certain certain duration tau is going to be the same no matter where that interval sits. So if this is an interval that has a certain duration and this is an interval that has the same duration, the probability of 3 arrivals in this interval is going to be the same as the probability of 3 arrivals in that interval. And therefore, since
This is constant. That's
this probability does not depend on where the interval sits, that probability will be fully defined by the number of arrivals that we're interested in and the length of the interval as opposed to the location of the interval. So we will be using this notation here to indicate this probability. In this notation, we think of tau as a constant and then P
um,
of k corresponds to probabilities. In particular, if you add over all k's, the various probabilities, what you should get would be a value of 1 because this exhausts all the possibilities. And k here ranges from 0 to infinity because we allow an arbitrarily large number of arrivals during a given time interval. Now, with this assumption in place, it would still be possible to have arrivals that happen simultaneously, multiple arrivals at the same time point. In order to avoid this situation, we introduce one more assumption, which is the following. It talks about the number of arrivals during a time interval that has a small length delta. During a small time interval, there is a negligible probability of having more than one arrival. We will either have 1 or 0 arrivals, and the probability of one arrival is a certain number, lambda times delta. It's proportional to delta, so if the interval becomes smaller and smaller, that probability also goes to 0, but it goes to 0 at a rate proportional to delta. So you can think of lambda as probability per unit time. These are the units of lambda. Now, here I'm writing an approximate equality. What does that mean? It means that these are not exact expressions, but they are exact within a second order term. And the second order term is a term that's negligible compared to the first order term when delta is small. More precisely, mathematically, what we mean is that a second order term compared to a first order term goes to 0 as delta goes to 0. Finally, let me reiterate that lambda should be interpreted as an arrival rate. It is a probability per unit time. The bigger lambda is, the bigger the probability is that we get an arrival during a small time interval. If we double lambda, then we double the probability that we have an arrival.
so let's see. So this is 2, right? Okay.
Arrival during a small time interval, and so we expect to have about twice as many arrivals. In what kind of situations does the Poisson process arise?
Probability mass function would be. I think this is like kind of mean squared variance.
In general, it arises whenever we have events like arrivals that are somewhat rare and which happen in a completely uncoordinated manner, so that
So where is Poisson? Let me guess. So the Poisson could be seen in. I don't know. I can't. I'm trying to think. Where could the Poisson be seen in machine learning? I think so. On average, I don't know. Poisson regression. So this is probability mass function? No way. Poisson distribution is a standard for um, probability mass function, Poisson regression, production model. It's, regression with count data, Poisson regression, part one. No, no.
Yeah, but then we're talking about Poisson regression, which after logistical regression is the most common sort of generalized linear model that you'll encounter in the wild. It's used to model counts. For instance, the number of eggs laid by.
Okay, how much? Yeah, okay. How much is it you? Call center analysis, predicting how much number. Okay, yeah. I think it's perfect for call center scenarios. E-commerce customers, regression, link function, prediction. So describe.
That they can show up at any particular time. In such situations, the number of arrivals will be
Linear with normal noise. Yeah, linear regression with like normal normal noise is just pretty easy to calculate. You just have to like do the distance formula and mean squared error. Try to like measure that the line, the best fit line. You have to like measure the best fit line. Okay. Let's look at this. Poisson videos.
often described by a certain distribution called the Poisson distribution, and which is named after the person who first studied this situation, who is a famous French mathematician by the name of Siméon Denis Poisson. An early example where the data seems to fit the description of the Poisson process is a curious one. It had to do with deaths from horse kicks, that is, accidental deaths, in the Prussian army. The idea here is that a death by a horse kick can happen pretty much at any time, and different arrivals, that is, different accidents, are completely uncoordinated from each other, so the process is sort of completely random. For more scientific applications, it was realized that certain physical phenomena obey the Poisson process. Examples are the following. You have some radioactive body which decays, and the decay happens by once in a while emitting various particles. Different particles get emitted at completely random times in a completely uncoordinated manner, and therefore this process is actually described as a Poisson process. Conversely, if you have a photo detector who looks at a very weak light source. So photons arrive from that weak light source one at a time, and you look at the times at which photons hit the photodetector, then the process of photon arrivals is very well modeled by a Poisson process. For more modern applications, if you look at the financial markets and the times at which certain very unexpected events, like certain market shocks, occur, a model that is commonly employed is to use a Poisson process model. Although this is not an entirely accurate model, it provides a first approach to
He actively. What is the example?
to situations like this. But these days, the predominant source of applications for the Poisson process is in various service operations. You are the phone company. Phone calls get placed at random times, and because there are several people involved who are uncoordinated with each other, those calls get placed at completely
Ooh, call center. I could do a ML model for call centers. Let's try this ML model for call centers.
random times, and the same
Stochastic queuing model and analysis of ML forecasting stochastic queue side. Yeah, I think I can do it. ML model.
In what kind of situations does the Poisson process arise? In general, it arises whenever we have events like arrival.
It's more arrival focus. And how did the actual formula come about? So I think it's just like the deriving of the binomial distribution. It's NLP inside live analytics for call center. Transform existing call center with the Gen AI machine learning in 15 minutes. How AI machine learning RAG solutions transforms call center operations. LLM, no. Can AI improve call center feedback performance? No, we don't care about feedback. Contact with artificial intelligence, cloud Cisco. No, AI call center prediction model.
So I worked at a lot of call centers. There's a lot of salaries there. You got like 50 bodies sat there making calls all day and kind of struggling because it's not that easy. We're reading off of scripts that, you know, we
I'd like to introduce our speaker for today's presentation, Igor Alcantara, Data Science and Education with IPC Global and Click. With that, I'd like to turn it over to our presenter. You can take it away from here.
All right. Thanks, Mega. Can you all hear me?
We can hear you perfectly.
All right. So again, I am Igor Alcantara. I work for IPC Global as Director of Data Science Education. As Mega introduced me, also Click Community MVP, Click Ambassador for social media. I work with Click and this type of technology for plus 20 years. And plus 20 years. And
Generative AI. Okay. You can use machine learning LLM RAG, reduce employee churn and HR employee retention case. The speaker pays. HR data under invoice shows about, let's say, those who review AK, meaning the company is losing many of its best people. Statistical tests confirm its difference significant. What are the ML models being used? Question mark. The demo mentions a familiarity rather than specific HR churn prediction case. Quick tries a range of classification algorithm. Like, is it using Poisson process? in this they're not using Person process for either HR. The call center using RAG over documentation, no arrival. What do they? Give me a video where arrival event count prediction model. I don't know. Putting AI to work for customer service. It's a lot of LLM voice pattern recognition type shit. Okay, shows how many Simon arrive two models fixed in linear. Poisson 4 process.
So previously we saw that the state variable nt of a count process, which satisfies the Poisson postulates, is Poisson distributed with parameter lambda times t for an interval of length t. And this fundamental result is why we refer to the process by that name. Now this result allows us to calculate probabilities associated with the counts of a Poisson process for a given configuration of observation scheme and parameters, and this in turn allows us to make predictions about the trajectories of such a process. Now, since we allow the process to increment at any point in the continuum of time, it is now natural to ask questions.
Stochastic Markov chain. Poisson.
So if you're wondering what the hell the long intro is all about, 1, your lecturer has a bad running habit. 2, we're kicking off counting processes today, and it just so happens that the best metaphor for trying to explain how counting processes work is a marathon. So let's jump in. Right, so we begin by formally defining a counting process. Now I know for some of you this might be a bit overreaching, formally defining the concept of counting, but as usual, we need to make clear what we're talking about when we transfer concepts to paper in mathematical language. In any case, later on in your postgraduate career, you'll see that counting process models actually can be quite formidable animals to work with. So here goes.
Why not? That's my question. Why not? Brilliant. Insurance. Okay. Website, app traffic, fraud, and security monitoring. Okay. Now we're talking number of suspicious. Okay. Right. Healthcare.
Stochastic process, which is just a set of random variables, nt, such that t is greater than or equal to naught, is a counting process if and only if nt denotes the total number of events that have occurred up to time t. Okay, so again, bit on the nose, but there you go. So let's look at some properties of a counting process then. Well, first, nt is a non-negative integer valued random variable. Okay, so this is a discrete process. We're counting things. 2, if s is some time less than time t, then, well, ns is less than or equal to nt. So that is the count at time s is less than or equal to the count at
So yeah, I'm maxing out the distribution today. Okay, I'm gonna take a small little break.
Yeah. I just wanted to give him some confidence. Get that bit where the light, fades from it. Come on, find the legs, Joe. Imagine you're coaching yourself. They're really small, right? It is, really small legs. Yeah. Yeah. It's got to be a pea-sized head. That's right. Yeah, it's hard to capture his Yeah. It's so nice. It's all the time. And then these fingers, just so my jaw doesn't crush. I am stuck. Because I'm not in a good position. Abba. In. Yeah, nice. I want to get it still with his legs completely up in the air. You got that pro on camera? Huh? Yeah, I did, yes. Yes. Oh. Dear. Why is he not tapping? Flipping awful. Oh dear, Geordie. We'll have to chin strap him. Yeah. It's just about getting with the move. Remember, Joe, you've got to teach him to do other things after this. We're about to teach him. What's wrong with your ligaments, man? That's mine was tapped about 20 hours ago. You would get out of there. Oh dear. Yeah, that's right. I can't get out of there, can I? I don't really know how you would get out of there. Much nicer. His hand's like the size of Joe's head. Breathe through your nose and nose, Joe. Was that on the head? Yeah.
Okay. How long was the break? Fucking hell, it was 40 minutes. 40-minute break. Ain't no way. Ain't no way. Okay, let's poison.
Same story goes about, let's say, service requests to a web server, service requests to any kind of company. So many applications that are being studied these days and which rest on Poisson models involve service operations of this type. The definition of the Poisson process gives us information about the probability that we get k arrivals during an interval of length delta when delta is a very small number. How can we find the probability of k arrivals during an interval of some general length tau, where tau is no longer a small number? In particular, we're interested in the random variable denoted n sub tau, which stands for the number of arrivals during an interval of length tau, and we wish to find the PMF of this random variable, the probability that n sub tau is equal to k, and which is what we have been denoting by this particular notation in the context of the Poisson process. Now, if instead of the Poisson model we had the Bernoulli process model, we would know the answer. S, the number of successes or number of arrivals in n slots, has a PMF which is given by the binomial formula. Can we somehow use what we know about the Bernoulli process to find the answer for the Poisson process? The answer is yes, and it involves a limiting argument of the following kind. We take the interval from 0 to t and divide it into a very large number of intervals, so many of them, where each one of the intervals has a length of delta, where delta is a small number. And to push the analogy with the Bernoulli process, we will be calling those little intervals as slots. Now, during each slot, we may get 0 arrivals, 1 arrival, but there's also the possibility that there may be 2 arrivals, or even more than 2 arrivals, happening during one of the slots. Because of this, the picture that we have here is not quite the same as for the Bernoulli process, because in the Bernoulli process, each one of the slots we get only 0 or 1 arrival. So the source of the discrepancy between the two models is that here a slot may obtain 2 or more arrivals.
Bro, now it doesn't make any sense. What the fuck? So, should I move on to the next one, or should I go deep into it? I don't know, it doesn't make any. Like, how do you derive that formula, though? That's like the most puzzling part of all of this. Is that how do you come up with the formula? How do you derive it? So, is it common? daily driver, a specialist. It's not as common, so I can kind of, I don't really, did I, fuck, did I just do that? Holy shit, I can't believe I just did that. Okay, let's look at another distribution, shall we? I think like bro, height is like the worst metric in all of this because we have people just like fraud matching their way into it. You know what I mean? Like, what's the study for?
Small number. How can we find the probability of k arrivals
probabilistic empirical probability mass function. Given the range of integers, draw a discrete distribution, implement a function to compute the empirical probability of mass function. The function should return the value probability. So this is what? So 1, 2, and 3. 1, we have like two values. 2, we have this probability density. This is how dense it is. Half the time. I think I can do it. I need to return this of this, comma this. Okay. I think I need to go for I in range. Should I go range? Yeah, range of length of samples. I need to go over everything, and I need to count them. I need to use the hash table. How do I use the hash table? Yeah, the hash table sums for some reason. It never. Come on, look upon me. Fucking bitch. Fucking hell. So how do I implement? Okay. Oh, she's not even using a hash table. But why does it know everything? It's a high likelihood this might actually work too. It's kind of like disturbing. You know what I mean? Like, what the fuck? So, what is going on with the hash table? I don't understand hash tables at all. I know I have to like use a hash table, value 1. Like, how are you appending? So total, so values in freq. So we're appending, okay, probability, okay, I got it. So usually it's like using two hash tables to calculate one, which is, okay, frequent. Explain this. Oh, which is incrementing. Okay, I think I can do it. But what the fuck is this PF? Sort key lambda x is to x 0. Is this one thing that got me tripping? Is this one thing that got me tripping? Mhm. Is this one thing that got me tripping? Is this one thing that got me? Okay, I think that's the empirical probability. Okay, PMF is the probability mass function. So it's the same as here. It's the PMF of the number of arrivals. It's going to be in a hash table. It's going to be, so let's say, okay, we can represent it that way, I guess. So it's going to be like, let's say on average, it's 5 people taking a shit. No, it's 5 shits a day, right? And K is given to be 3. And so let's say on a scale with 2 days, right? This is 2 days, and we have 5 shits. In 2 days, we have 5 shits, and we're calculating the probability of k is 5 when this lambda is equal to 2. And the probability mass function of both of those days is going to be, on first day, on 1, it's going to be 3. On 2, it's going to be 2. On day 2, it's going to be 2. So the probability density is going to be, should I like divide it? Is that what's happening? I think I should divide it. No, I think I'm dividing the frequency. So 1, what? Okay, 1 divided by 5. Okay. 1, no. Okay, 3 divided by 5, 3, 2 divided by 5. That will give me the, so this will be 3 divided by 5. So this is for day 1. And day 2 is going to be, the probability mass function will be 2 divided by 5, which is, yeah, you can do it in a this kind of thing. And obviously, this ensures safety. So that's probability and statistics. Probability. Mm, let's do lead code. A little bit of lead code. Probability. Probability and statistics. Where is probability again? Is that it? Toss a coin. Let's try this. How do we figure this shit out? Alice plays the following game loosely based on the card 21. Alice starts with the point 20, 0 and draws. What are we supposed to find? What is the probability of fewer points? Okay, this is like 2. I'm punching 2 above my weight class. Not good. Hacker rank. Probability. Where's probability? Bro, my rank is brutal. The rank is getting brutal day by day. System design. Nah, I need a probability. Where can I do some probability sums, bro? Ability sums like lead code? Question mark. It's gonna give me Kaggle, which is Code Force is gonna do it. That's Poise distribution is calculating the occurrence. And formula is kind of Mm, probability. Yeah. Okay. 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 Doop, 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 doop. So suppose 80% of the Netflix user rates the movie thumbs up of the time and thumbs down. So given someone 3 movies in a row, a thumbs up, what's the probability that they're a lazy rater? Hmm, interesting. Bro, brutal. Is lint code that good? Computational geometry is pretty good. Kaggle. How do I filter this shit? Oh, I need to like do a lot of DP. Fuck. DP. Yeah, DP. Need to max out on DP to get good at that. So stat learn. Okay, let's just move on to the just to Poisson. Calculate the conditional probability of data, expected value, distribution sample of a mean. I think I can do this. Write a function that demonstrates the sampling distribution of a mean of the mean. The function takes as input the number of samples and the sample size and the distribution type, uniform or exponential. Okay, it should return the mean of the sample means. So we're finding the means of the sample means. Return the mean of the sample means. So we have a couple of means given, and we find the mean of that. I think requirements for uniform. Draw the uniform 0, 1 using NP random uniform. Okay. For exponential. Okay, we have uniform exponential. Is that what? I think it is. Uniform exponential and gamma. Okay. Gamma distribution. What the fuck is gamma distribution? Who knows? Okay. Generate num samples, independent samples, each size samples. Compute the mean of each sample, then return the mean of all samples. Okay. We are given simulate 100 samples are given. No, okay, 100 number of samples and the sample size is 30. So it's like, and you have distribution, uniform distribution. And we're trying to find the mean of the mean. Huh? Okay, sample distribution of mean. Let's look into it.
The definition of the Poisson process gives us information about the probability
Sampling distribution of mean, sampling distribution of the fast version.
StatQuest! Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about sampling a distribution, or getting samples from a distribution. This is something that we do all the time in StatQuest, so I wanted to make a video that we could reference rather than covering the same material over and over and over again. So let's get down to it. Here, we have a histogram of height measurements. Each red dot represents a different person that we
Fuck these motherfuckers, I hate them.
measured. The tallest part of the histogram shows the region where measurements are most likely. In this case, most of the people we measured were between 5 foot 7 inches and 6 feet tall. The low parts of the histogram show where measurements are less likely. In this case, we didn't measure many people that were shorter than 4.5 feet or taller than 6.5 feet. We can approximate the histogram with a smooth curve. You guys already know all this from the StatQuest on statistical distributions. What we want to know today is what it means to take a sample from a distribution. All that means is that we use a computer to pick a random number based on the probabilities described by the histogram or the curve. For example, if we wanted to take one sample from this distribution, there's a good chance the computer will pick a value near the middle, where the histogram and curve are tallest. However, every now and then, the computer will return a value from the edges, where the histogram and curve are the shortest. Why would you want to take a sample from a distribution? We do this to explore statistics. The computer can generate lots of samples, and we can plug them into statistical tests to see what happens. Since we know what the original distribution is, we can compare our expectations of what will happen to reality. For example, I could take two samples, where n equals 3, from a single distribution and do t-tests on the samples. In this case, n equals the number of measurements we take within each sample. Since the distribution is the same, the t-test should give me a large p-value. Doing lots of tests will give me a sense of how frequently the t-test successfully gives me a large p-value.
In this video, we'll be learning about the sampling distribution. But before we talk about sampling distributions, we need to know the difference between a sample distribution and a sampling distribution. So let's go through an example. Suppose we have a population of 10,000 people, and we know that the mean height of everybody in this population is 5'4".
Bro, are we like talking about ancient Sparta or something? Like ancient Rome? The fuck?
Recall that a sample is a small portion of the population that we examine.
They're talking about Philippines. These Filipino men, 5'1" Filipino.
And draw conclusions from. So from one sample, the average height could be 5'3", but in a different sample, the average height could be 5'7" or 5'4". Notice how the sample mean doesn't always have to be equal to the population mean. This is because samples are relatively smaller in size, and because of that, they have more variability, contain less information, and don't always accurately represent the population. So what's the difference between a sample distribution and a sampling distribution? A sample distribution
Sample is the entire thing. Sampling distribution is like a collection of, like an array of like a distribution.
Involves taking a singular sample from a population and
Okay, with that knowledge, let's do this. Write a Python function that demonstrates sampling distribution of the mean. The function should have been taken input is uniform or exponential. It should return the sample mean. Okay. Uniform or exponential. Uniform distribution. Explain to it. What the fuck is this? This is uniform distribution, I guess.
Hey guys, it's Mark from Ace Tutors. And over the course of the next several videos, I'm going to explain some of the most common probability distributions covered in statistics. In this video, I'll go over the uniform distribution. So first off, a uniform distribution is characterized by having a constant probability within.
So I think this could be like a male or female, right?
In a certain domain.
It's binary.
But what does this mean? Well, to find out, let's take a look at this distribution on a graph, where the x-axis represents the different values this certain event can be, while the y-axis represents the probability of those events. From this graph, you can hopefully see how each x value within the domain of a to b has the exact same y value, which implies the same exact probability. But what is this constant probability? Well, we already know that if we add up all the probabilities of all the outcomes of a certain event, or in other words, find the total area under any probability distribution, the result must equal 1. Since this area is a nice and simple rectangle,
So if it is a rectangle, the area is going to be length into breadth. So it's length is equal to 1, breadth is equal to 1, whatever. No, don't do that.
we can find its area by multiplying its height by its width. Now we can.
So let's say we have a curve. So that's when we use maybe like a curved function or something. Like that's when we use.
We can solve this equation.
Calculus to find what? Calculus to find the sampling distribution, right? The sampling distribution or the probability function.
For what the height must be. Dividing both sides by b minus a, we get that the height of this distribution must be 1 over b minus a.
Why? Why? Why should it be? Why should it be 1 over what? Exponential distribution. It's not really like used to be. Is binomial, normal, Poisson, and categorical multimodal distribution is like the most used.
Okay, now that we covered the general look of the uniform distribution, let's go over some common values associated with this distribution. First, let's find its mean, or expected value. Because the distribution is nice and symmetric, the mean, mu, ends up being right in the middle of its domain, which you can find by taking the average of the domain bounds, aka a plus b divided by 2. And once again, from the distribution symmetry, this value ends up being the same for the median. Okay, moving on to standard deviation.
That's the mean and the median because it is a perfect, it doesn't have any bias towards left or right. Right, that's the uniform distribution.
This formula ends up being a little less intuitive. For a uniform distribution, the standard
deviation okay, it's plus or minus square root. Maybe it's the square root gets cancelled because it's an actual square, right? So plus or minus 1 by b2, I don't know.
Standard deviation sigma ends up being the square root of b minus a squared.
What the fuck? How did he come up with that? Bro, motherfuckers just make up shit. Like, so that is uniform distribution. So that's okay, that makes sense, kinda. Okay, kinda makes sense.
Divided by 12. Next, let's go over some of the fun stuff, probability. When we discuss finding probability for continuous functions like this, we generally want to find the probability of a range of things occurring. For example, we might want to find the probability of our event's outcome being between C and D. To calculate,
You need to take length, height divided by the breadth, length into breadth. And the height, I think it kind of like remains the same because it's just this side is a probability. So if we know the distance between these two, so it's going to be height divided height into thing. So we know the height and the distance formula, I think.
Like this, we could approach it one of two ways. You can either see it as a rectangle and calculate the area by length times width, or, understanding that the distribution is uniform, you can find the fraction that the desired interval makes up the entire distribution's domain. Either way, you would end up with the same result of D minus C divided by B minus A.
Yeah, you could do that. Of course.
Now that we covered some general terms from the uniform distribution, let's put
Yeah, okay. He did it the other way.
the theoretical garbage aside and see how this works with a concrete example. Say that you take the bus to work, and every day the bus is uniformly late between 2 and 10 minutes. On any given day, how long can you expect to wait? And with what standard deviation? Finally, if the bus is late more than 7 minutes, you'll be late to work. So what is the probability that you'll be late on any given day? Okay, first, let's set up our graph. Instead of A and B, we can replace these values with 2 and 10 because that's the entire domain for the bus's arrival time. Now, let's start solving some of these questions. First, we want to find how long we can expect to wait for the bus.
Fucking bitch. Poisson, sampling distribution, exponential distribution, implement prediction distribution, monitoring, negative binomial distribution, sampling distribution of mean, Poisson normal distribution. Okay. Types of distribution. Central limit theorem, sampling mean distribution. That's the, you have uniform or exponential. I don't know the meaning of both.
A uniform distribution describes a situation where each event is equally likely to occur. Therefore,
It's independent though, isn't it? So uniform distribution.
graphs of uniform distributions always have a rectangular shape, because the likelihood of every event is the same. Rolling a dice is an example of a discrete uniform distribution, as each side of the dice is equally likely to show up. An example of a continuous uniform distribution could be what time the next bus arrives when you know it arrives every hour, but you don't know when the last one left. Let's imagine this bus example and ask ourselves 4 questions. Number 1, what is the probability density function? Number 2, how do we draw a continuous distribution graph? Number 3, what is the likelihood of us having to wait between 5 to 20 minutes? And number 4, what is the mean and standard deviation? To answer the first question, we need the formula for the probability density function, which is fx equals 1 divided by b minus a. In this formula, 1 is the total probability of all possible outcomes, i.e. 100% or 1. b is the upper bound, or the maximum amount of time we must wait, and a is the lower bound, or the minimum amount of time we can wait for the bus. This means that the probability density function can be written as 1 divided by 60 minus 0. Moving on to the second question, to graph this, we will simply mark where points A and B are on the x-axis, and the point where the probability density function is
The mean is going to be 30 then.
on the
Mean and
y-axis.
median.
Then we draw a rectangle including all 3 points. In other words, the rectangle will include all possible events and their probabilities. Then for the third question, to find the likelihood that we will have to wait between 5 and 20 minutes for this bus, we'll simply draw a smaller rectangle in the same way. So in this case, A will be 5, B will be 20, and the probability density function will still be the same. Then we simply calculate the area of this new rectangle. So the base equals 20 minus 5, which is 15, times the height of the rectangle, which is still 1 divided by 60. So 15 divided by 60 equals 0.25 or 25%. For the final question, the formulae for the mean and standard deviation are mean equals a plus b divided by 2, and standard deviation equals b minus a divided by the square root of 12. So if we plug in those numbers, we see that the mean in this situation is 30 minutes, and the standard deviation is 17.321 minutes. However, it is worth 5, which is 15, times the height of the rectangle, which is still 1 divided by 60. So 15, same way. So in this case, A will be 5, B will be 20, and the probability density function will still be the same. Then we simply calculate the area of this new rectangle. So the base equals 20 minus 5, which is 15, times the height of the rectangle, which is still 1 divided by 60. So 15 divided by 60 equals 0.25 or 25%. For the final question, the formulae for the mean and standard deviation are mean equals a plus b divided by 2, and standard
Like,
deviation.
how do you derive it? That's like the more important question. So what the fuck is this? For I, if the distribution, the fuck? For I in range, number samples, if the distribution is equal to uniform, okay, if it is uniform, data random, uniform, 0 to 1, if the distribution is exponential, data n random exponential 1 by sample size, raise error, unsupported distribution, append. Okay, like, what the fuck is that how we do it? Just like, okay, it's just like random thing that we do. Okay, that makes very little to no sense. For range, so we're just iterating over the entire list, and we're if it is raise unsupported distribution, and the sample means dot append for like thousands of data, and we're just spitting out the float at the end. Float and the mean. I think that's what they're asking for. This is asking the mean for the mean random exponential. What is It's about generating random data using NumPy. If you're asking what do they do, random exponential zero. Okay. Okay. Scale parameter of the mean distribution. What does exponential data look like? Plot them in a graph. Uniform expo. .py. This is like a retarded question. Give me a pretty retarded example too. Give me code, bro. Are they gonna give me fuck you? Okay, we got some. That's figure one. We have an exponential distribution. Scale is equal to 1. Okay. What would yeah, a uniform distribution. Kind of okay. It kind of looks like uniform. So let's raise the sample size. It's gonna look better, I think. And scale is 1. Okay, looking good. Looks better. Let's. So the more the sample increases, the better it gets. I don't think it's gonna work, but let's give it a shot. So it has better and perfect, right? Now samples. Let's do scale 2. What does scale do? Who knows? Oh, it's exponential. Ten. What are the arguments? What is? Let's take 1,000. So the function random number gets uniformly distribution. Okay. High low size. What? General form. High maximum value in your case 1. Okay. Oh, I think, is that what it is? Just plotting the thing. Exponential high. What is high? Okay. It shows the scale is 1, but it's not. Scale 1000. I don't know. Go on. Oh, this is the scale. Don't know what that means though. What does the bottom row mean? Who knows? Let's tweak this. I think I know what's about to happen, but that is uniform, so we never know. So this is exponential. Okay, let's do 100. Stop this shit. Stop code. Stop.
Welcome to Mutual Information. My name is DJ. In this video, I'm going to show you what I think is the best approach to learning about probability distributions. I'll start with an analogy. Let's say you had a full minute to memorize this mess. After that minute, you have to redraw it from memory perfectly. Every edge, every node, no mistakes. You think you can do it? Well, if you have a normal human brain like me, then no, there are just too many details to get wrong. But what if I were to tell you about the pattern behind this complexity? That is, there are 25 nodes, which can be numbered like this, and you should consider only nodes that are not prime. Then draw an edge between any two of them, but only if their difference is prime. Now, I'll ask again. Could you redraw this pattern knowing this fact? I mean, yeah, almost certainly. It might be tedious and annoying, so please don't do it. But yes, it could easily be done all from memory. The lesson here is, if you want to hold something big and complicated in your head, it's best to find a simple compressed pattern that explains all or most of that complexity, and then learn only that pattern. Then, when it's time to produce that complexity, just reapply that pattern. Now, this lesson isn't always easily applied. How to explain a complicated thing with a simple set of rules isn't typically obvious, or possible. Fortunately, it happens quite frequently in mathematics, and in this case, statistics. So, to state it directly, my argument is, if you want to understand a bunch of probability distributions, it's best to focus on the stories that relate them, rather than their individual definitions. Now, because the world of probability distributions, their properties, and their relationships is huge, the compressed pattern that relates them is still quite big. Compression helps, but to own such a huge, valuable bag of information, you still must pay with focus, time, and patience.
Ooh. So Poisson. No, the fuck. It comes from the binomial distribution. Binomial and Pascal distribution and gamma Poisson power series. Okay, this is when n is infinite, meaning the number of trials is basically infinite. And the average is okay, the average is whatever, and we just like computing the whatever normal distribution. Bernoulli binomial. What the fuck is binomial? So normal Gaussian. The fuck is Gaussian? Where the fuck is uniform? Bro, this is fucking beautiful. Oh my god. This is fucking beautiful. Uniform distribution. Uniform, U. Where is U? Standard uniform. So we have standard uniform distribution. It kind of goes into exponential power and exponential distribution, and it also kind of goes to beta distribution. Okay, normal. Okay, it's such a big leap. Standard triangle. Benford. Legit, bro. This is. Oh my god. This is the best resource ever. Is the future of linear algebra random? Oh my god, this guy, bro. Like, who the fuck is he? Like, I gotta... Quantitative researcher. Oh my god. This guy is a fucking... Oh my, senior research scientist, machine learning engineer and founder. Holy. Holy, bro. Straight goat. This is like goat level material. Okay. We have okay, I need to like get familiar with uniform and exponential. Yeah, nothing like the normal distribution, isn't it? Uniform, expo. The fuck is exponential? Okay, I need to like max out normal distribution. Normal and Poisson. So luckily the Poisson and binomial has some nicely like goes into normal distribution. Let's see normal distribution. Where is multi-model, categorical multi-model, categorical, categorical. What the fuck is multi-model and categorical distribution? Where is multi-model min-max? No. Min-max, I think it's okay. Bro, this is the truth nuke. You know what I mean? T. What the fuck is T? What even is T? Who knows? Logistic, inverted, gamma, gamma inverted, gamma, okay, exponential. This is discrete. Rectangular. I mean rectangular and uniform. Uniform distribution is somewhat of a rectangular distribution. Why isn't the uniform distribution square? Categorical. What is categorical? Categorical slash multi-normal distributions name question mark? No, I'm not trying to like use any. or generalized Bernoulli is a multimodal distribution of the general. Okay. The multimodal distribution keeps the same name, multimodal distribution. The categorical distribution is also called multi-Looney or generalized Bernoulli distribution. So Bernoulli generalized G, where is G? Generalized gamma, generalized normal, gamma normal, uniform, so the uniform distribution Bro, why did he do that? It's so fucking useful now. I gotta learn all this. If not, I'm a terrorist. This is the greatest thing about distributions ever. Statistics. Exponential family Gaussian process, regression, linear regression explained in 12 minutes, bias variance trade-off. Bro, the fact that no one knows this, oh my god. Exponential family, factor analysis and probabilistic, I don't know. Monte Carlo of policy reinforcement learning, cool. Too much I'm not ready for reinforcement learning like that. What happens of the boundary? Most important and surprising result from the information theory. Future. Okay. So this is pretty great. How? Okay. Distributions, random variables, probability rules, exceptions and variance, samplings and empirical measures, central limit theorem, hypothesis and testing, confidence interval, correlation and regression. Bottom line, shape of the data, which order to learn it first. Probability basics, random variables. Nah, fuck that. Key distributions. This is exactly where I'm starting. Bernoulli beta distribution. Fucking beta. Best stats and probability goes for ML. Question mark. The part of mathematics and machine learning. Okay, where can I? What the fuck? Can audit for free, no payment requirement to watch lectures. Mhm. Is convolution a normal distribution thing? beta. Beta. So normal distribution.
With focus, time, lines above each blue box, the distribution with these. Okay, what about the exponential? But it was only when I learned that fact did I start to get comfortable with the student t distribution. The student t is just a bunch of normal.
So I need to get really good at whatever this shit is. The most by percentage. Fucking in DS and ML. Okay. Used. Mutual information. Information. Normal distribution. Gaussian process. Gaussian distribution. Fisher information. Okay, that's how important normal distribution is. Okay.
Sometimes it feels like the universe is just messy. Um, normal distribution. Let's go.
A 1,000 people walk into a bar. You measure their height as they enter. If you plot those heights on a histogram, something curious happens. Most people fall in the middle, with just a few outliers on either side. Tall, short, but mostly average. This creates a smooth peak. Now for something less human. Picture a baby elephant. Scratch that. Picture a whole herd of newborn elephants, each standing on a scale. Plot those weights. Same smooth peak. Different species, same shape. Okay, one more. Look at the daily revenue of Cafe Socratica over a year. Some days are great, some are quiet, but most hover around a typical number. Plot those, another smooth peak. This keeps happening. Everywhere you look. People, animals, money, all kinds of measurements. The same general shape shows up. A curve with one peak symmetrical, tapering off to both sides. It's so common we gave it a name. The normal distribution. We picked the name normal for this distribution, not because others are abnormal, but simply because this distribution is so common. It happens all the time in nature. Informally, the shape of this distribution is sometimes called the bell curve, because it looks like the outline of a bell, round on top, tapering smoothly down both sides, and made of polished brass. The word distribution is a very important mathematical term. It's hard to summarize in just one sentence, so most people point to a graph of the distribution. What the graph tells you is which data are common and which data are rare. It's like a map of possibilities. The taller the curve at a particular point, the more frequently those values tend to appear in the data. On the other hand, where the curve is low, that means those values don't come up as often.
So that's the variance and standard deviation, the top and the bottom. So in a uniform, what will be the standard deviation? It's just going to be the
For some reason, it's by 12. I don't know why.
This isn't fortune telling. The distribution doesn't tell you what will happen. It tells you what values are typical and how much room there is for surprise. The normal distribution
B minus A divided by square root of 12.
in particular tells us that values tend to cluster around a central point. The farther you get from the center, the less often those values occur. We don't want to give you the wrong idea. We're not saying all normal distributions are identical. The height of people, the birth weight of elephants. You can tell the difference between these distributions. The peaks of these distributions occur at different values, and they taper off at different rates. So how can you describe which normal distribution your data has? Turns out you only need two numbers, one for the peak and one for the taper. These two key numbers control the bell shape of any normal distribution curve. The first is the mean, written with the Greek letter mu. This is the average, the center of the distribution. It tells us where the peak sits. The second is the standard deviation, written with the Greek letter sigma. This tells us how spread out the values are. A small standard deviation means the values are tightly clustered. The curve is tall and narrow, dropping off sharply. A large standard deviation means the values are more spread out. The curve is lower and wider.
So yeah, the standard deviation is pretty large for female intelligence. For male intelligence, it's pretty clustered and it's pretty narrow.
With a gradual taper means the values are more spread out. The curve is lower and wider with a gradual taper. These two numbers, tall and narrow, dropping off sharply. A large standard deviation means the values.
So the standard deviation for male intelligence is pretty narrow and small, and the standard deviation for female intelligence is pretty large and pretty spread out. So that's why, I mean,
Values are more spread out. The curve is lower and wider with a gradual taper. These two numbers.
but that doesn't mean IQ in itself is real. That just means that's how it's spread out, right? That's we can infer with, again, IQ in itself doesn't tell if a person is smart or not. It's just like you can infer a lot of things with that. And if you can, again, IQ varies a lot, it differs a lot, but we know if someone measures a 70 IQ, more than likely that guy's like lower in the intelligence, right? We cannot, if someone like, yeah, you can like do it in their own language, this and that, but it's like if someone measures 70 IQ, the probability of them being like that being wrong and them actually being like 120 IQ, whatever that means, right? Whatever the number means, is pretty. It's pretty rare. It could be like 80 IQ or 90 IQ or 100, right? That is like, again, it's still like, if you actually look at the data, it's still like not possible. It's still like a really unlikely for that shift, the probability shift to happen. But it's much more realistic. We could say if again, you can take the variance, right, the closest, and you go, okay, it's somewhere in between this, and that's the idea, right?
Mu and sigma define a normal distribution. The mean specifies the center of the bell curve.
And the thing is, if you like go and play chess and all of this thing, it might like put you in the higher end. I don't know.
Curve. The standard deviation stretches or compresses it horizontally, shaping how concentrated or dispersed the values are around mu. Together, they give each normal distribution its unique identity. Change either one, and you get a different bell curve. So now you've got your bell curve, you know where the center is, you know how wide it is. But here's the real power of the normal distribution. Once you know mu and sigma, you can start making predictions. How likely is it for a value to land near the mean, or far from it? The answer, surprisingly predictable. In any normal distribution, most of the values fall within just a few standard deviations of the mean. This is called the empirical rule, and it gives us specific percentages. Roughly speaking, about 68% of the values fall within one standard deviation of the mean. About 95% fall within two standard deviations, and about 99.7% fall within three. This means that if a value is within one sigma of the mean, that is within one standard deviation, it's still pretty typical. There's another way scientists and engineers describe events that are less common, and we show this graphically by highlighting the long tails. A 2 sigma event refers to data that lie at least 2 sigma away from the mean. This should make you think something a little unusual is happening. 3 sigma, that means at least 3 sigma away from the mean, and that's truly rare. In fact, the phrase 3 sigma event has become shorthand for something unlikely, but not impossible. You may hear scientists talk about 5 sigma events, meaning extremely rare. So rare they might signal a real discovery, or a problem with your data. 6 sigma often comes up in engineering and quality control. You can see how the normal distribution gives us a common language.
So yeah, 1 sigma means it's pretty typical, 2 sigma means it's kind of rare, 3 sigma, pretty unlikely to be occurring in nature. 4 sigma, engineers work in 6 sigma, right? That's where the quality testing and all of that comes to fruition. Like if you take dangers and like if you take, let's say, dangers and 99, if it's 99.999% normal and the 6 sigma has some sort of defect, or I don't know, like the plant might blow up or something, you need to take that in consideration. That's why even in data, 6 sigmas, engineers usually work with 6 sigmas
language for describing how surprising or unsurprising data is. Let's make this a little more personal. Suppose we measure the head circumference of a large group of adult humans. For men, the average head circumference is 57 centimeters, with a standard deviation of about 2 centimeters. For women, the average is 55 centimeters, with a standard deviation of roughly 1.5 centimeters. If head sizes are normally distributed, and they mostly are, we can apply the empirical rule to both groups. For men, about 68% have head circumferences between 55 centimeters and 59 centimeters, within 1 standard deviation of the mean. 95% of men have a head circumference within 2 standard deviations, that is, between 53 centimeters and 61 centimeters. And if you want to include 99.7% of men, the 3 sigma range is between 51 centimeters and 63 centimeters. Now for the women. About 68% have head circumferences between 53.5 centimeters and 56.5 centimeters. That's within 1 standard deviation from the mean. You'll find 95% of women fall within the 2 sigma range, between 52 centimeters and 58 centimeters. To cast a wider net, look within 3 standard deviations. About 99.7% of women have a head circumference between 50.5 centimeters and 59.5 centimeters. If you have a tape measure handy, you can measure your own head and see where you land. Do you have a 1 sigma, 2 sigma, or 3 sigma head? The empirical rule lets you quickly grasp how common or rare any individual measurement is. Thanks to all the generous people supporting us on Patreon. Their contributions make Socratica possible. YouTube ads help to some extent where the center of the data is. We also need to know how spread mean. Add up all your values and divide by the number of values. You're only halfway there. The mean tells us where the center of the data is. We also need to know how spread out the values are. That's where the standard deviation comes in. You compute the standard deviation using this formula, where the variance is the average square distance from the mean. To calculate the variance, we subtract the mean from each value, square it, then take the average of those numbers. Once you have the variance, you take the square root to get the standard deviation. Now you might wonder, why do we have two different numbers that measure the spread of the normal distribution? The variance gives us an intuitive way to measure spread. By squaring the differences from the mean, we ensure that all the values are positive, which makes sense when we're talking about distances. But there's a complication, units. If your data is in centimeters, then the variance is in square centimeters. That's harder to interpret. So we take the square root. This gives us the standard deviation, a number that still reflects the spread. Now it's back in the same units as the original data, just like the mean. That makes it much easier to understand and compare. This is what allows you to describe a real-world data set with just two numbers, the mean and the standard deviation. Once you have those, you can sketch the bell curve, apply the empirical rule, calculate probabilities, and much more. To demonstrate these calculations, let's compute the mean and standard deviation for the heights of the 11 footballers who played for England in the 1966 World Cup final. First, we calculate the mean height. Add up all the heights, 1,948 centimeters, divide by 11 players. The average height is 177.1 centimeters. Don't forget the units. Notice that the average height is in centimeters, just like the individual heights. Next, we calculate the variance, subtract the mean from each height, square the result, add them up, and divide by 11. This gives us 36.0826 square centimeters. We'll round this to 36.1 square centimeters. Again, pay close attention to the units. While the mean is in centimeters, the variance is in centimeters squared. And to get the standard deviation, we take the square root of the variance. That gives us 6 centimeters. Did you double check the units? Because you should really double check the units. The standard deviation has the same units as the mean, centimeters. A collection of numbers describing a population are often called summary statistics, or summary stats for short. Here are the summary stats we calculated for the 1966 World Cup champions, those sons of England 11 Lions who brought immortal glory to their land and carved their names into the annals of history, not merely by the strength of their legs, but by the measure of their hearts. So far, the mean and standard deviation seemed like independent ideas, center, spread, but in fact they work together, combining into a single formula that precisely describes the bell-shaped curve for the normal distribution. This is called a probability density function, or PDF for short. The PDF gives you the shape of the curve. It tells you how values are distributed, where they are common, and where they are rare. But how do you actually use this formula? You use the PDF to calculate the probability that a value falls within a certain range. Specifically, the probability that a value lies between two numbers a and b is the area under the curve from a to b. Finding that area usually requires calculus. You compute an integral. Luckily, you don't have to do that by hand. Software can do it instantly, and most calculators and statistics tools have built-in functions for working with the normal distribution. After seeing this highlighted region under the curve, now we can better understand why this is called a probability density function. Think about how we talk about density in physics. Density tells you how much matter is packed into a space, but you never ask.
So yeah, like I think that is okay. That's when like the three-dimensional calculus, multivariable calculus comes in to measure the area of like a three-dimensional curve. With that, okay, that makes sense.
Ask how much matter is at a
Makes
single
more
point.
sense.
Instead, you ask how much matter is in a region. It's the same idea here. The PDF gives you a probability density along the number line. At a single point, the probability is 0. What matters is the total amount of probability across an interval. For bonus understanding points, notice the formula has that fraction in front. It makes sure the total area under the curve adds up to exactly 1, meaning 100% probability. Remember these key takeaways. The graph of the PDF is the familiar bell curve. The area defines the probabilities, and the mean and standard deviation are the control dials for the system. 8 greater than or equal to 7.
Bell curve or central limit theorem. Is central limit theorem, bell curve the same thing? Okay, that makes sense. Normal distribution. I need to pitch. Pitch a back a macoma. Waking up a mac. Normal distribution. Central limit theorem. Bayesian interference. I don't know what that means. Normal continuous derived normal distribution. Derived distribution.
You may have heard the phrase, the unreasonable effectiveness of mathematics in the natural sciences. This was the title of a paper by the physicist Eugene Wigner, but even more fun than the title is the way that he chooses to open it. The paper begins, quote, "There was a story about two friends who were classmates in high school talking about their jobs. One of them became a statistician and was working on population trends. They showed a reprint to their former classmate, and the reprint started as usual with the Gaussian distribution. And the statistician explained to the former classmate the meaning of the symbols for the actual population, the average population, and so on. The classmate was a bit incredulous and was not quite sure whether the statistician was pulling their leg. How can you know that, was the query. And what is the symbol over here? Oh, said the statistician. This is pi. What is that? The ratio of the circumference of a circle to its diameter. Well, now you're pushing the joke too far, said the classmate. Surely the population has nothing to do with the circumference of a circle. In the paper, Wigner then goes on to talk about the more general phenomenon of concepts in pure math seeming to find applications that extend strangely beyond what their definitions would suggest. But I would like to stay focused on this particular anecdote and the question that the statistician's friend is getting at. You see, there is a very beautiful and classic proof that explains the pi inside the formula for a normal distribution. And despite there being a number of other really great explanations online, see some links in the description, I cannot help but indulge in the great explanations online, see some links.
Gaussian distribution.
This
Normal like multivariable calculus. No. Gaussian distribution. I need to max out Gaussian distribution.
The basic function underlying a normal distribution, aka a Gaussian, is e to the negative x squared. But you might wonder, why this function? Of all the expressions we could dream up that give you some symmetric smooth graph with mass concentrated towards the middle, why is it that the theory of probability seems to have a special place in its heart for this particular expression? For the last many videos, I've been hinting at an answer to this question, and here we'll finally arrive at something like a satisfying answer. As a quick refresher on where we are, a couple videos ago we talked about the central limit theorem, which describes how as you add multiple copies of a random variable, for example rolling a weighted die many different times or letting a ball bounce off of a peg repeatedly, then the distribution describing that sum tends to look approximately like a normal distribution. What the central limit theorem says is as you make that sum bigger and bigger, under appropriate conditions, that approximation to a normal becomes better and better. But I never explained why this theorem is actually true. We only talked about what it's claiming. In the last video, we started talking about the math involved in adding two random variables. If you have two random variables, each following some distribution, then to find the distribution describing the sum of those variables, you compute something known as a convolution between the two original functions. And we spent a lot of time building up two distinct ways to visualize what this convolution operation really is. Today, our basic job is to work through a particular example, which is to ask what happens when you add two normally distributed random variables, which, as you know by now, is the same as asking what do you get if you compute a convolution between two Gaussian functions. I'd like to share an especially pleasing visual way that you can think about this calculation, which hopefully offers some sense of what makes the e to the negative x squared function special in the first place. After we walk through it, we'll talk about how this calculation is one of the steps involved in proving the central limit theorem. It's the step that answers the question of why a Gaussian and not something else is the central limit. But first, let's dive in.
Oof, okay. Okay, I need to take a break and come back to normal distribution. I need to basically max out normal distribution and everything around it, and kind of go from there. Yeah, okay. I need to max out normal distribution first. Max out normal distribution. Go back to some statistics, maybe. I don't know. Let's actually look at this. This is probability, random processes, 10x, steady state, Markov, finite, Bernoulli, Poisson, both classical. So Bayesian interference. So this is all like Bayesian statistics, I think. Fundamentals. discrete and random. This is all undergraduate too. That's even the depressing part.
They're now fucking drinking all day. Oh my god. I wanna like, it's like, I would like to go to sleep. I'm just like, I don't know why. Just wanna. But I guess, you know, you can pick from over there.
certain festival. Well, why is everybody so terrified of this?
Forwardly. What's the time? So let's say I come at 6. That I think that'll be decent hours, I think. Okay. Normal distribution. Credit for dealing with imbalanced datasets. Okay, blacked out like a phantom. This phone keep having a tantrum. Emo, get a party like. Blacked out like a phantom. This phone keep having a tantrum. Emo, like a party like. Blacked out like a phantom. Pen. Base deeply. Random variable. Important distribution. Joint. Conditional distributions. sampling and estimation, central limit theorem, confidence, hypothesis testing, linear regression, Bayesian linear regression, Bayesian optional, multi, that's normal distribution, maxing out normal distribution today. Perfect question. We can precisely programming, business logic, and reasoning pillar. Mhm. Mhm. Okay, normal distribution.
The full formula solution between two Gaussian functions. I'd like to share an especially pleasing visual way that you can think about.
Is I mean, it could be represented in 3D. That is one option to do for sure.
Okay, fucking idiots. Idiots, idiots, idiots. Doomer, doomer, doomer. Yeah, business logic, data science. Oh, I'm cooking. I'm cooking with this one. What did I plan today? Always narrow down one foot at a time. Okay.
This calculation, which hopefully offers some sense of what makes the e to the negative x squared function special in the first place. After we walk through it, we'll talk about how this calculation
upper bound, lower bound. I don't understand the upper bound.
All right, welcome back to 61200. We continue probability, and not only that, we continue on expectation today. We'll also get to a second measure of random variables, which is variance. But first, most of today will be expectation. Remember what we did.
Predicates, sets and proof, cryptographic graphs and coloring matching. Bro, these are all retarded shit. Like, why would I use that? So retarded. Random variables as types. Probability mass density, right? Probability function. Probability density function. PMF, probability mass function. What's the difference between PMF and PDF? I mean, I could like watch a video. PMF versus PDF.
So probability theory enables us to reason about our uncertainty. Now, a key distinction that informs how we handle a particular random variable is if it's discrete or continuous. If we're ever dealing with a finite set of possible values, say a categorical label from an animal classification model, then this is a discrete random variable.
Is classification discrete or let's look at this. Classification discrete or continuous? ML. Pretty sure it's discrete.
But discrete random variables can also apply to infinite target spaces as well, specifically countably infinite, like the natural numbers. Some of our intuitive notions of probability from everyday life transfer over to discrete probabilities, where we can think of the probability assigned to each possible state as the fraction of times that particular state is likely to occur. For example, say it's late, we're tired and hungry, and we're randomly picking a piece of fruit out of the fridge, with an equal chance of picking any particular piece. If we have 3 apples, 1 pear, and 4 oranges, the probabilities of picking each type of fruit are 3/8, 1/8, and 1/2 respectively. We represent these with a probability mass function, or PMF, essentially a list of probabilities for each possible state.
PMF. Let's see. Probability mass function is it just the mean given in a, I think I know what it is.
For any discrete distribution, the probabilities must all lie between 0 and 1 inclusively, and sum to 1. That is the total probability.
So yeah, probability always lies between 0 and 1. And sigmoid function is a type of logistic regression where it is either 0 or 1, right? Either you get a match or you don't get a match. In like the case of Tinder.
Must be 1. Now a quick note on notation. We use both of these to refer to the probability of the random variable big X taking on a particular value little x. When we have multiple discrete random variables, we can visualize the joint distribution as a table where entry ij contains the probability of both xi and yj occurring. If we define a new random variable z as the tuple xy, then z's target space is the Cartesian product of both x and y
calculate the unigram probability of from corpus. Probability conditional joint. Okay. Chi square. Calculate the conditional probability. Compute the total possible. Okay, Bayesian interference is different from Bayesian statistics. Okay, I need to remember that. Empirical probability mass. Yeah, this makes no sense, but that is the probability mass. Okay, this is the probability mass. We're given bunch mean, and we're just calculating how likely each of them are meant to be. Pretty straightforward. You're just dividing it. Okay. Where is my video? Yeah, this is the
target spaces. So here there would be 15 possible states. Our constraints from before still apply, and the sum
probability distribution explained clearly.
of all the probabilities must still equal 1. In a multivariable,
Yeah, if you add all of them, or if you add all of this will equal to 1, because probability should always equal to 1.
setting like this, the marginal probability of one of the random variables
Who came up with that? Why is it 100? You know what I mean? Like, if it's 100, I don't know, I think it's like much more useful. You can much more easily visualize if it's 100, I think. And just percentage in general, right? 100 percentile, 99th percentile.
say x, taking a particular value, regardless of
Today's video covers probability and probability distributions through purely visual means. And so leaving this video, you should be able to understand what a random variable is, the concept of a probability mass function, a cumulative distribution function, as well as a probability density function. And so let's...
So that is like the main random variable.
Let's jump right into these 4 topics. Let's start off our conversation with discussing the idea of rolling a die. And when I roll a die, there are a series of outcomes that are possible, each of which has an associated probability. And so the idea of rolling a die is a good example of a random variable. It's simply some random phenomenon that can be represented by numerical values. And so if I roll a die, it can take on a value between 1 and 6, and there's some uncertainty around what the outcome will be. Now, to represent the probabilities associated with those different outcomes, that's where a probability mass function comes in. And so a probability mass function simply is a mathematical representation to highlight the probabilities associated with the different outcomes that a random variable can take on. And so the way that this probability mass function will look like is that on the x-axis are the different outcomes that this particular random variable might take on, and on the y-axis we show the different probabilities associated with those outcomes. And so in the example of rolling a die, there are going to be 6 outcomes that this particular random variable can take on, and we usually weight each one of those outcomes with a probability of 1 over 6. Now, if you studied probability and heard that a probability mass function is associated with discrete random variables, hold that thought. We'll come back to that in a second. But now you should know what a random variable is, as well as a probability mass function. The third item I want to introduce now is the idea of a cumulative distribution function. Similar to a probability mass function, we have a plot where we're plotting probabilities on the y-axis, and on the x-axis, the outcomes for the random variable. However, unlike a probability mass function, where we're simply plotting the probabilities associated with each one of these outcomes, in a cumulative distribution function, we are plotting the probability that this random variable will take on a value less than or equal to that outcome of interest. So let's see what this looks like in the example of rolling a die. One way to visualize what's happening in the cumulative distribution is that we're running a sliding window across a probability mass function and simply adding up the probabilities associated with each outcome that our window passes by. So up until the outcome of 1, the cumulative probability, the cumulative distribution function, should be equal to 0. And that is because it's impossible for us to roll a die and have the outcome be less than 1. Now, when we hit the value 1 with our sliding window, what is our new estimate of the cumulative distribution function? It should be 1/6. In other words, there is a 1 in 6 chance of the outcome less than or equal to 1. Now we can continue sliding our window, and up until the outcome of 2, all outcomes have a 0 probability set to them. And so the cumulative probability remains at 1/6. And when we hit the value 2, there is now a jump again in our cumulative distribution to 1/3. There is now a 2 in 6 chance of the outcome less than or equal to 2. And I can continue this process. The cumulative distribution remains constant up until the outcome 3, where again it jumps up to 1/2. And I repeat this process, running the sliding window across the outcomes for the probability mass function, summing them up and mapping that to the cumulative distribution function. And notice that the cumulative distribution function ends at 1. There is a 100% chance that when I roll the die, the outcome will be less than or equal to 6. In fact,
Discrete, right? Continuous? No? So this is it looks similar, right? Looks exactly the inverse, so that makes sense. So let's do 50%. Okay, 50% looks similar. Obviously normal, uniform. Uniform is like the most. So on this point, it's exactly 5.5, right? What is A? A is the length. So the length is -5. Mean variance. Whoa, wait, what? Wait, what? It's still okay. Is it half though? So yeah, I think playing around with it. What does 50% look like? See, 50% is always going to be 50%. It's always going to be the median. It doesn't really matter where the thing is getting stretched out. 50% is always going to be 50%. That's cool. This is 50%, right? Like 50% is going to always remain as 50%, and variance is just this one variance would be, why is it 12? I don't understand why is it 12, but I understand the squared thing. It's just a minus b, so all the both of the distance squared. So variance is it's like the distance formula divided by, it's pretty okay, it's the distance divided by, it's this distance divided by 12, and I don't know why it is 12, but it is 12. So the standard deviation, the sigmoid standard deviation function is going to be square root of the distance formula divided by square root of 12. Well, I don't know why. Why is it 12? I don't know. Could be any number of reasons. Let's say a square plus a square, 2a square, and you put 1. Doesn't really matter. 2, 4, 14. So what is the cube? Oh, well, we're not cubing, we're squaring. So I don't really get why this like that. Normal chi-squared exponential. exponential mean 1 divided by mean. So 1 divided by the average. How are they like deriving this formula? I just don't get it. Like, how do you derive that? Genuinely, binomial chi-squared probability, calculate the conditional probability, KL divergence, Gaussian distribution, central layer theorem. Okay, sampling mean distribution. It's basically the mean distribution of things. It's similar to probability density function, where we have using fucking bitch joint mass function, probability mass function, hypergeometric distribution, probability mass function. Okay, binomial distribution, probability normal distribution, PDF calculator. Okay, normal distribution. Bro, so many normal. What is KL? I don't know what is KL. KL diverges between two normal. Your task is to compute the Kullback. The fuck does that mean? Genuinely, what does it mean, bro? Divergence between two normal distribution. KL diversion measures how one probability distribution offers a second reference probability distribution, writes in KL diversion nonce sigmoid. Okay, we have all these sigmoid. Sigma p is just like the variance, I think, and variance of one probability mass function, one normal distribution, variance of another one. And what is mu? Mu is just an average, I think. Mean is mu. So let's put this shit. Kullback-Leibniz divergence. Georgia Tech. Short introduction to entropy and clock. KL divergence. KL divergence. Okay, this is KL divergence. Okay, cool. Data science behind it. What is KL divergence?
The Kullback-Leibniz divergence is a distance measure between distributions which is widely used in information theory and particularly for machine learning. The equations come in two forms, one for discrete probability distributions and one for continuous distributions. On the surface, however, it's not exactly clear why the KL divergence is so useful, or even how the summation or integral.
Discrete will be the summation of things 1, 2, 3, 4. Continuous will be like a continuous thing. Continues towards infinity, positive infinity or negative infinity. So, okay, go on.
Measures the distance between distributions in any way. To explain why the KL divergence is a very natural idea, let's back off and consider what it is we're trying to achieve. What we're trying to do is measure the distance between probability distributions. Let's first give an example of a probability distribution. Let's imagine that we have a fair coin which is equally likely to be on heads or tails. This means that the probability of heads is 0.5 and the probability of tails is also 0.5. Let's imagine that we also have a bias coin where the probability of heads is set at P and the probability of tails at Q. Can we say anything about how similar the distributions are to each other? There isn't a
KL. What is KL? Kullback. KKK. Interesting.
trivial answer to this question. We might be able to make general statements about which examples are closer. For example, if p is 0.55, then coin 2 would clearly be much closer to the fair coin than if p was 0.95. Why? Well, the results we see with 0.55 would be quite similar to the fair coin, and it would be very easy to confuse them. However, if p was 0.95, then differentiating between the two coins would be quite simple, and could be done in merely a few coin flips. Determining the difference between two extreme examples might be easy, but can we make any quantitative statements about how different they are, and is it possible to put a numeric value on the distance? Previously, we reasoned that a natural way to think about the distance between distributions was to look at how easy it was to confuse them. A basic way of measuring this might be by seeing if the distributions assign similar probabilities to the same sequences, as if they assign similar probabilities to similar sequences, it implies that the distributions aren't too different. Let's then propose an algorithm. First, we generate observations using coin 1. We then calculate the probability of coin 2 generating observations. After that, we can compare this probability to the probability of the true coin generating the results. If the output probabilities are similar, then the coins might be similar. But if the likelihood is significantly smaller for the second coin, then the coins might be very different. A natural thing to calculate would then be this ratio here, which compares the likelihood of the observations for each coin. Let's go over an example of the proposed method. Assume that we have a coin with probability p1 for heads and p2 for tails. We then flip the coin n times and record the observations. We then work out the probability of coin 1 generating the sequence. Working this probability out is quite simple. Whenever we see heads, we just multiply by p1, and whenever we see tails, we multiply by p2. Let's now introduce coin 2, which has probabilities q1 and q2 instead. Working out the probability of coin 2 generating the data is done identically, where we just multiply by q1 for each heads and q2 for each tails. These two expressions can then be simplified by realizing it's the product of the probability of each outcome raised to the power of the number of occurrences. For the first coin, this is p1 to the power of the number of heads multiplied by p2 to the power of the number of tails. We then want to find the ratio of probabilities, so we simply divide the first likelihood by the second one. Although these calculations may seem unrelated to the KL divergence, believe it or not, under the hood the KL divergence measures the exact same thing. To see how, let's normalize for sample size by raising it to the power of 1 over the number of samples, then take the log of this expression. We'll then turn on the log rule autopilot and bring down exponents, turn multiplications and divisions into additions and subtractions, again drop down the powers, which gets us to this stage. Note that if observations are generated by coin 1, then as the number of observations grows to infinity, we expect the proportion of heads to tend to p1 and the proportion of tails to tend to p2. This
What the fuck am I looking at? Okay, let's duplicate this. I don't understand this. So you have term 1 is the sigma q, the sigmoid function of both of them. And term 2 would be the sigmoid function squared plus this mean minus, okay, divided by sigmoid 2. And KL divergence is equal to term 1. So KL divergence is log of sigmoid p divided by sigmoid q minus 0.5 minus sigmoid p squared plus mu p mu q bracket divided by 2 into sigmoid p squared sigmoid p squared minus 0.5. Okay, that's the solution though. Like I'm just memorizing the KL divergence. Give me the math formula. So this is the formula for sigmoid. So difference in spread. That makes sense. Y log, I don't understand it. And different in mean. variance mismatch. Whatever that means. Minus 1.2. Minus 1.2 is just whatever. Yeah. Multivariate class, k dimension. If it's 3 dimension, is summation. What the fuck am I looking at? Is it 3D? Is 2 example 3D question mark? Multivariate class is not specifically for k dimension in normal distribution. What does it mean? Gaussian k reduces to 1D. So when is it 3D? Covariance matrix, and your covariance matrix. So here actually happens. What the fuck? Higher dimensions, not just 3D. So what is k? What is multivariate? Question mark. Core concept, unvariant, one variable, bivariant, multivariant, usually 2 plus. Number, height of people, not just one person. Unvariant, height, number, age. So it's multidimensional. Summation. So it is multi-dimensional compared to normal DKL. Divergence, exactly, okay. Unidivergent, 1D is one variable. Oh, why is it even 1D? It should be 2D, right? Multivariable, okay. I don't know. Does KL only work on what does KL only work on? Does KL only work in normal distribution? Question mark. Probably not. General definitions of K. This is like a general one. So this is for KL. Summation of P of X log PQ Q. Okay. Continuous. This is for discrete. Fuck. Discrete. Counting. It's 1, 1, 2, 3, 4, 5, and continuous is going to be D KL P of Q. Integration, of course. Why didn't I think of that? Integration of log PQ Q dx. So let's take continuous distribution like so how would it be? Okay, this is continuous. Let's go discrete. Does the summation come? No, I didn't use any summations for this. Not integration. I don't know. So how does it look for binomial? That's my question. You can compare K between, okay. KL is pretty important, I guess. Setup, suppose, just show, oh, wait, what? Binomial PMF. KL discrete case for binomial. Interesting. This is KL for okay, divergence KL for binomial would be That checks out. Okay. Give me for every distribution important in DS and ML. Exception trick. What is DL? What is KL? There's no single closed KL formula for every distribution. No, I mean like KL. So this, oh fuck, poison. Okay, that makes sense. That kind of makes sense. Kind of makes sense. Normal, Gaussian, multivariant, normal distribution, multi. How does this look? Normal. Standard, normal, multi. Where is multivariant? Multi. The fuck is normal? So is poison the mean? How does poison look? How does poison look? In a graph, okay, when the average is really large. So when the average is really large, like how large are we talking? Most textbook use better approximation, very good approximation. I guess n normal. Okay, n is normal. So example 2, very skewed type now. Okay, important. Okay, close to normal. Visualize, because I'm a hardworking motherfucker. Ready when you are king. Okay.
This allows us to say that in the limit, nh over n is p1, and nt over n.
KL divergence is just What the fuck is scalar divergence? I don't know. Cross entropy. I think cross entropy is something talked about in this pitch. Look like an angel, look like an angel. Normal distributed PDF, probability dense. I think there's going to be a lot of calculus involved. Just saying. Standard deviation. So yeah, I think there's a lot of calculus involved in this. Just thinking. Yeah, there's no way I'm like coming up with that solution. Coefficient, exponent, coefficient, exponent. How do they derive the thing? Normal function. I think there's like more to it that they're not like saying to me. You better say that shit to me, bro. What more are there? 2D normal distribution. Let's go.
Even the best dart players never throw with perfect aim. Each shot lands a little high or low, a little left or right. Over time, these errors lead to a scatter of points on the board. If we keep throwing and recording each impact, the pattern becomes clearer. Near the bullseye, the points are dense. Farther out, they get sparser. Imagine dividing the board into small sections and counting how many darts land in each one. At first, the counts look random, but gradually a structure emerges. Stack those counts vertically, and you see something remarkable. A smooth hill, highest in the center, gently tapering off in all directions. This is the two-dimensional counterpart of the bell curve, a bell surface.
Bro, that's three-dimensional. What the fuck?
And just like in one dimension, the shape is not an accident. It's the natural mathematical description of random variation in two directions, the 2D normal distribution. Normal distributions are not just for darts. They appear in nature, engineering, finance, and almost every field that measures real-world quantities. Take woodworking. Suppose you cut 1,000 boards, each meant to be exactly 1 meter long. No matter how careful you are, the cuts will vary a little. Some boards will be short, some long, but most will be close to the target. Here, the measurement, the board's length, is a single number. That makes it one-dimensional data. If we plot the histogram of these lengths, it rises into a familiar shape reminiscent of the bell curve. This suggests that our data is normally distributed. That means we can use the data to estimate the mean and standard deviation, which allows us to graph the associated bell curve.
Mean is just like the middle value, standard deviation.
This bell curve is a probability density function, or PDF. In practice, the PDF gives us a way to figure out the chance of getting a board in any range of lengths. Let's return to our dart game, which requires math in 2D. With darts, the location of each throw is described by two numbers, how far left or right it lands, and how far up or down. So one number for the horizontal and one number for the vertical. That's an x-coordinate and a y-coordinate for each hit. In the woodcutting example, a single number was enough to describe the variation. For darts, one number is not enough. You need both coordinates to tell the story. When data have two dimensions like this, the normal distribution often shows up again. In the woodcutting example, the board lengths follow a bell curve. And curves are one-dimensional shapes. For the dart example, the distribution of the hits give rise to a smooth surface in space. And surfaces are two-dimensional shapes. This shape captures how likely each combination
Okay. One-dimensional curve visualized in two-dimensional space. That's what I'm talking.
of x and y is to occur. For our one-dimensional example, the mean was a single number, the point right in the middle of the bell curve. But when we move into two dimensions, the middle is no longer on a line. It's a point in a plane. We describe this point with two numbers, the mean in the x direction and the mean in the y direction. Together, these form.
What is the mean in normal distribution in the first place? Language model. Nah. analysis, multivariable calculus, whatnot. Okay, subscribe. Brit, Bree, the mad guy.
This shape is known as a bell curve, or we might call it a Gauss curve. It's super important for many reasons. One of the most popular applications is the normal probability distribution. This symmetrical shape describes a lot of phenomena in the real world. And the way we use it to find probabilities is by measuring the area under a curve between different values. We have to account for some normalizing constants, but really this shape comes from this function e to the minus x squared. And you know, if we want the area under this curve, well, we're going to have to do some integration. And this function, I don't know how well I've drawn it, but it stretches forever to the left and to the right. It has an infinite domain, so we want to integrate this thing over its entire domain to find the area. So this is now our problem, the definite integral from minus infinity to infinity of this function, e to the minus x squared dx. And what you may notice is that none of the regular integration techniques work very well here. There's no like u substitution or integration by parts that's going to be able to solve this. And we could use a power series, but that's going to get a little bit clunky. That's maybe how we would do it if it wasn't a definite integral, if we didn't have any bounds. So here's the trick, here's the technique. We're going to just call this I for integral, and I'm going to square both sides of this equation. I'm going to square this entire integral. Not something you're used to doing, but what does something squared really mean? Well, it means times itself. So this just means the definite integral from minus infinity to infinity of this times itself. Now, a subtle trick here that this quantity, it doesn't really matter that I called it x, right? We could have used t's or z's or y. Y's, and I'm going to use a y here to represent the other one. And it's completely equivalent because when we actually integrate this, well, all the x's go away, don't they? Think fundamental theorem of calculus. We end up just plugging in for x. So it doesn't, don't they? Think fundamental theorem of calculus. We end up just plugging in for x. So it doesn't matter what letter we use here. I'll just call y on the second integral, and these are being multiplied. But it's the same quantity. They're both I, so this is I squared. And actually, since both the letters are completely different here, and they have the same definite bounds here, minus infinity to infinity, this is what's known as separable. These integrals are separable. If you go into multivariable calculus, you might try to split up these integrals to make them easier. Here we're going to combine them. So this is exactly the same thing as a single definite integral, putting these both inside the integrand. So they're both base e. When we multiply like bases, we add the exponents. So minus x squared minus y squared, that's the same as minus x squared plus y squared in the exponent. And then we have, I really should need two integrals here. We're integrating twice. We're putting these together. And I'll just say dy dx. If you've had some experience in multivariable calculus, you might know where we're going next. This is still a pretty wonky integral to solve. It's in rectangular coordinates that's making it wonky, a square coordinate system. But x squared plus y squared, think Pythagorean theorem, think trig, think of fundamental trigonometric identity. X squared plus y squared is r squared. The Pythagorean theorem, we're going to make a change of coordinates here. We're going to switch to polar coordinates. Instead of using rectangular, we will use the trig functions and the Pythagorean theorem to change this coordinate system and these bounds. So forever to the left and forever to the right. Well, for r boundaries, the r always starts at the origin, namely at 0, and then, in this case, continues out forever. So these bounds, the r bounds, will be 0 to infinity. And
That's a root out of thing that I just wrote down. I need to cut that shit down. Normal distribution. Z-score.
The mean vector. Another way to think of the mean vector is as a pair of coordinates that tells us where the center of the Bell surface is located. If the mean vector is 0, 0, the surface is centered on the origin. If it's 2, negative 3, the whole surface is shifted 2 units to the right.
Applied math and data analytics. Okay, let's go. Ah, don't do that. Control Z, can I do Control Z? Fuck. Deep. Deep learning. Calculate the covariance matrix. What the fuck is covariance matrix? Oof. Why is everything so difficult? Okay, anyway. Okay, we know what this means. Text preparation, accuracy versus prediction. Bro, why is everything like so difficult? Oh my god. But that's what I need.
And 3 units down. Remember when we cut boards? The mean gave us the typical length. Here, the mean vector gives us the typical dart hit, the spot where throws tend to cluster. The mean vector is like our anchor in 2 dimensions, the reference point around which everything else is measured. The mean vector tells us the center, but it says nothing about the shape of the surface. In 1 dimension, the bell curve was described by 2 numbers. The mean told us the location of the center, and the standard deviation told us how wide the curve was. Location and spread, that was all we needed. But a 2-dimensional surface is richer. The location is described by the mean vector, but for the shape we need 3 pieces of information: the width in the x direction, the width in the y direction.
So this is what is a 2D? What is a 2D normal distribution called? What is a 2D normal distribution? Bivariant. Okay, fucking bitch. Bivariant. I mean, let's take normal distribution. Non-centric, log, normal, binomial. Okay. I still don't get what binomial is. Structured normal. What the fuck is this? Grungery.
Even the best dart players never throw with and whether the shape leans. Taken together, these 3 numbers fully describe the way the surface tapers off in all directions. Mathematicians organize these numbers into a grid called the covariance matrix. On the diagonal are the variances, the spreads in the x and y directions. Off the diagonal sits the covariance appearing in both positions. Why use a matrix? Because once you move beyond 1 dimension, vectors and matrices are the natural language for describing data. They make it possible to extend these same ideas to 3, 10, or even hundreds of dimensions, all using the same framework. In finance, two-dimensional normal distributions occur frequently. For example, observe the daily stock prices for Oracle and Microsoft. Side by side, their prices often move up or down in a similar fashion. But instead of focusing on the prices themselves, let's look at the percent change in price from day to day, what we call the daily returns. We'll arrange these daily returns in pairs, one number for Oracle and one for Microsoft for each trading day. If we display these pairs of returns on a scatter plot, we get a shape that's not just a random cloud. Instead, we see a kind of tilted oval pattern. When Microsoft has a good day, Oracle often does too. And the same goes for down days. Based on the shape, we see that we can model the relationship using a two-dimensional normal distribution. The center of that oval is the mean vector, two numbers, the average daily return of Microsoft and the average daily return of Oracle. The covariance matrix then describes the shape of the spread. The variances tell us how volatile each stock is on its own. The covariance captures how much the two move together. So with these 5 numbers, the 2 from the mean vector and 3 from the covariance matrix, we have a clean mathematical way to describe how these two stocks move together. Not every single point will fit perfectly, but the 2D normal distribution gives us a nice summary of the pattern. What comes to mind when you hear Socratica? For some, it is the spark of a new idea. For others, it is a carefully crafted explanation. This is what Socratica means to us: creativity, depth, craftsmanship. Function, or at a single point, that is always 0, but the density of
Normal PDF, okay.
probability in a region around that point. In one dimension, the probability of landing in some interval was the area under the curve across that interval. In 2 dimensions, the same idea applies, but we have to update our language. Instead of a curve, the PDF is now a surface, and instead of area under a curve, we need the volume under a surface. To find the probability of data appearing inside a certain region of the plane, we compute a double integral of the PDF over that region. The formula for the PDF of the 2D normal
Double because there's two
normal distribution is a concise way of packaging the 5 parameters, the mean vector and
so the mean, what is the variance will become covariance, and standard deviation. What is standard deviation of 2D? What is standard deviation of this? Okay, normal covariance. Uh,
perfect.
okay, that makes sense.
And the covariance matrix, the 5 numbers we discussed earlier, determine the entire surface. The details of evaluating double integrals are usually covered in a calculus course. In practice, the computation is handled by software. What matters is understanding the idea that the probability in 2 dimensions comes from volumes under the surface, not just areas under a curve. Let's put the 2-dimensional PDF to work, returning to our stock pair, Microsoft and Oracle. Here is the mean vector we calculated earlier and the covariance matrix that went with it. Together, they define the PDF, the surface hovering above our scatter plot. Suppose we want the probability that Microsoft's return lands between 2 bounds, and at the same time, Oracle's return lands between its own bounds. That region shows up here as a rectangle. To find the probability of being inside it, we integrate the PDF over that rectangle. In other words, we calculate the volume under the surface above that region, carry out the double integral, and we get the probability. Now let's try the same idea with darts. Here is the mean vector and covariance matrix modeling a world-class player's throws. He has both high accuracy and precision. With those values, the PDF again gives us a bell-shaped surface. If we want the probability of landing in the bullseye, we define that region as a circle centered at the origin. Then, just as before, we integrate the PDF, this time over the circular region. That volume under the surface gives the probability of a dart hitting the center target. In both examples, the process is the same. Mean vector and covariance matrix define the PDF defines the surface, and probabilities come from integrating over the region you care about. We started with the familiar one-dimensional normal distribution. Just 2 numbers tell the whole story, the mean and the standard deviation. Then we stepped into 2 dimensions. Suddenly we needed 5 numbers, 2 for the mean vector and 3 for the covariance matrix. That might sound like a big jump, but it really is the same idea, just extended into a higher dimension. Here's the encouraging part. If you understand the 2D case, you already have all the tools for the general case. An n-dimensional normal distribution has a mean vector with n numbers, and a covariance matrix with all the pairwise covariances. The picture becomes harder to draw, but the mathematics is exactly the same. So this is not the end of the story. It is just step 2 on the road to the most general, most powerful version, the n-dimensional normal distribution. You're ready.
N-dimensional. Multivariate normal distribution. Holy shit. Multivariant. Okay, I think I'm feeling confident a little. Univariant and bivariant normal distribution. Okay, still I don't know what Okay, that is too little too advanced. Normal distribution. What the fuck is normal distribution, bro? This is covariance given of a sort of a is covariance. This is covariance matrix of is it a is it the same idea? Is it, what is covariance matrix?
What is up, everyone? In this video, we're going to be talking about a pretty intuitive and also really cool concept in data science called the covariance matrix. As you might have guessed from the name, the covariance matrix is just a big matrix that's filled with various covariances between variables in our data. So let's go ahead and look at a simple 2x2 case of the covariance matrix to get a feel for how it's constructed. Okay, here is our setup as always. We are researchers and we are trying to figure out if there's any link between the happiness someone derives from eating an apple versus the happiness they derive from eating a banana. So we go out into the world and gather 3 test subjects. You usually want more, but this is a toy example. We have our 3 test subjects, and they are enumerated in this table here. So just for how you read this table, test subject 1 is this first one. They get 1 unit of happiness from eating a banana, or 1 unit from an apple and 1 unit from a banana. Test subject number 2 gets 3 whole units from an apple and nothing from a banana. And oddly enough, test subject 3 gets -1 from eating an apple and -1 from a banana because they really, really don't like fruits. Okay? So let's go ahead and represent that by vectors on our apple banana grid right here. So we have the first one as 1, 1. That person would be 1, 1. The next one would be 3, 0. So let's go ahead and live on the apple axis right there, 3, 0. And the last one would be at -1, -1. So that lives right here. So our goal is trying to figure out whether there's some kind of covariance between the apple and banana variable. If it's been a while since your last stats class, or if you're a little bit fuzzy on the idea of covariance, just think of the covariance between 2 variables as the degree to which they go together. So if one of them is really positive when the other is also really positive, and vice versa, it's really negative when the other is really negative, they have a high degree of covariance. If on the other hand, one is really, really positive while the other is really, really negative, and vice versa, then they have a very low negative covariance, right? If that sounds a lot like correlation to you, it's because it basically is. Covariance and correlation are very, very similar, even up to their mathematical formulations. It's just a matter of correlation is bounded between -1 and 1, whereas covariance is not necessarily bounded between -1 and 1. Okay, so you can think of covariance in the same way you think of correlation, just with that slight caveat. Okay, so now let me erase the side of the board and let's go ahead and talk about how do we construct a covariance matrix for this setup. Okay, so your first step in constructing a covariance matrix for any kind of setup you might have is identifying what.
So confusion. What the fuck is confusion matrix then? It's something to do with machine learning.
Should the dimension.
Wait, what is confusion matrix again? I think confusion matrix. What the fuck is confusion matrix? Used in machine learning classification. Oh, that's the confusion matrix, huh? Okay. Okay, confusion matrix is similar to like Bayesian looking thing. Is it used in CNN? Convolutional neural network. Short answer. Oh, what the fuck? Where is it? I think fraud detection is one. Batch normalization, adjust the mean variance using. Okay. Whitening of rare in case. Okay, bro. What is it? It looks like Sanskrit. It's the histogram.
Of this covariance matrix B. Okay, so covariance matrices are square because they capture the correlation.
Log normal distribution, gamma distribution. Wait.
So you know how factorial works, right? You take a number like 5 and multiply it by 4, then by 3, then by 2, then by 1, and you get 120, which we write as 5 factorial. It starts small with 1 factorial equals 1, 2 factorial equals 2. But then it explodes really quickly, and by the time you reach just 4 factorial, you're already at 24, and 5 factorial shoots up to 120. Now here's where things get weird and kind of mind-blowing. What if I asked you to calculate 3 halves factorial? Like, what's the factorial of 1 1/2? Your first instinct might be to say, that's nonsense because factorial is defined as multiplying all the integers from n down to 1, and 1 1/2 isn't an integer, so how could you even compute that? But mathematicians being mathematicians, they found a way to make sense of this question, and the answer involves one of the most beautiful functions in all of mathematics. The basic idea is actually pretty intuitive when you think about it. We know what factorial is for the integers, so we have these points. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and so on. If we plot these on a graph, we get these isolated dots, and the natural question becomes, can we draw a smooth curve through these dots that would tell us what happens between the integers? Now you might think, well, I could draw any
Exponential.
curve I want through those points, and you'd be right. I could draw a nice smooth curve, or I could make it wiggle and oscillate between the points while still hitting each factorial value exactly. So we need some extra constraint to pick the right curve, and this is where the magic happens. The factorial function has this beautiful property, then factorial equals n times n minus 1 factorial, and we want our extended function to preserve this relationship not just for integers, but for all values. When you enforce this recursive property, along with something called log convexity, you get exactly one curve that fits. But how do we find this curve? Let's work it out step by step. We want a function f that satisfies f of x equals x times f of x minus 1, not just for integers, but for all x. Now, many functions in mathematics can be written as integrals, so let's try f of x equals the integral from 0 to infinity of some function g of t and x dt. If we plug this into our recursive property, we get integral of g of t and x equals x times integral of g of t and x minus 1. For this to work, we need g of t and x equals x times g of t and x minus 1. The simplest function that does this is g equals t to the power x minus 1 times some function h of t that doesn't depend on x. But wait, for our integral to converge, we need h of t to decay to 0, where gamma of gamma function. When you do the calculation, 3 halves factorial turns out to be 3 times the square root of pi divided by 4, which is
Cool. The gamma distribution.
Welcome back. Okay, so in the last lectures, we have introduced this exponential distribution and related it to the Poisson process. So roughly speaking, if you have a string of events that come in at some rate lambda, like emails, let's say, and so these events happen at times t1, t2, t3, and so on, and there are waiting times or arrival times between each of these events, we know that each of these arrival times or waiting times are exponentially distributed random variables, and the number of events I expect to see in an amount of time t is a Poisson distributed random variable with parameter lambda times t. That's pretty straightforward, really intuitive, made a lot of sense. There is a generalization of the exponential distribution. So exponential distribution gives me these waiting times between events. There is something called a gamma distribution. I'm going to write it over here, I think. There's something called a gamma distribution. Sounds really cool. A gamma distribution. Which essentially gives me the waiting time for the rth arrival. The waiting time for the rth arrival is going to be a gamma distributed random variable. Okay, so I might know, I know the waiting time for the next email is going to be exponentially distributed, but how much time do I have to wait for the 10th email from now? It's not just, necessarily 10 times my exponential distribution. It doesn't work like that. So we have this this variable t, and I'm going to call it, maybe I'll do it in blue because this is a waiting time. So this tr, the amount of time I have to wait for my rth email arrival, is going to be the sum of r waiting times. It's going to be omega1 plus, let's call it w2 plus dot 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 plus wr. And we are going to say that this random variable tr is distributed according to the gamma distribution. I'll write it down in a minute. Gamma of r comma lambda. So this has 2 parameters. The exponential distribution just had 1 parameter lambda. Gamma has 2 parameters, lambda and the number of events I want to be waiting for. Okay, pretty simple idea. Now, deriving this gamma function is a little bit messy. I'm going to give you the broad brushstrokes, and I'm going to omit the nasty math in the middle. And if you like, you can do it yourself and derive this from those steps. But you don't have to. You can just take my word for what this distribution is if you like. Okay, so the way that we compute this distribution is, again, we rely on a Poisson process. We say the probability that the waiting time is greater than some t, some little t, is equal to the probability of my Poisson process. Let me write this down. The probability that my waiting time tr is greater than some specific time t is equivalent, this is an equivalent statement, that the number of events that happen in t, less than t, is less than or equal to r minus 1. So this is equivalent to the probability of my event some t has to be less than or equal to allocated. Poisson, this is actually a cumulative.
Hey everybody, today we're talking about the gamma distribution. This is a continuous probability distribution that's most frequently used to model waiting time for a certain number.
Gamma distribution, that's continuous. Okay. Man, if people take kids with me, then it was my bank account. I got so much anger in me. Take it. Think I'm stuck in the matrix. Where the fuck's my nitrous? Yes, I'm a cucker. People were fine, but see what I'm saying? That and niggas. Niggas. Hanging with my cousin reading dirty magazine. Been seen some niggas kissing. That's when I give my cousin hey, give my cousin hey, give my cousin hey, give my cousin hey. What language? That's the sim maths. Gamma. Oh, it's just gamma. Okay. Delta, epsilon, zenda, theta, eta, theta, iota, kappa, lambda, mu. Okay, mu. Mu is mean. Nu is gi, omni, pi. Is it Latin? Sigma, tau, epsilon, epsilon, pi, chi, fisci, omega. Greek, is it Greek? Why Greek? Greek letters. Latin, Greek. I guess Greek dudes, they all like came up with it. Bro, nothing is like named after Newton. Isn't that crazy? Oh shit. So that's gamma. So if we tweak the K, I don't know why it does that. It wiggles in that way. Shit. So let's say we have this shit, and the theta is obviously the angle of the. Why does it? I want to visualize it though. Like this is like some retard memorized formula type shit. Like why does it do that? So when the angle gets bigger, there's something going on. There's something going on when the angle goes like that. I don't know why, but anyways, how long have I been doing it? Okay. Okay, another break. So I've been studying for like 6 hours, maybe. Definitely not 6 hours. More like 5 hours, maybe. Yeah, the first hour was just basically nothing. So 4.5 hours. I need to get another hour and a half. That will be what? That'll be six, bro. 6 hours. 6 hours a day. Fuck no. Embarrassing. 6 hours a day is embarrassing.
well, low-key do that. I don't think I can do this.